What if the universe isn't the chaotic, random expanse we often imagine, but instead operates with a precision so extraordinary it feels almost purposeful? Picture this: every star, every planet, every cosmic event aligning with such mathematical perfection that it challenges everything we think we know about reality. These aren't just interesting curiosities, they're cosmic coincidences so precise they defy probability, and they're scattered throughout the universe in ways that continue to baffle scientists and philosophers alike. From the perfect alignment of our moon and sun during eclipses to the inexplicable fine-tuning of fundamental constants that allow life to exist, these patterns suggest something profound may be at work in the cosmos, something that goes beyond mere chance or accident. Today, we're embarking on an extraordinary journey through 27 of these mind-bending cosmic coincidences, each one more astonishing than the last. We'll explore how the exact positioning of celestial bodies creates conditions so ideal for life that it feels almost orchestrated, and how the fundamental laws of physics appear to be perfectly calibrated for our existence. These aren't just abstract concepts, they're real phenomena that have shaped our universe and made our very presence possible. As we dive into each coincidence, we'll uncover the science behind them, the mysteries that still perplex experts, and the implications that connect us all to the very fabric of space and time itself. This exploration will challenge your perspective on the cosmos in ways you never thought possible, inviting you to question whether we live in a random universe or one that's remarkably designed. You'll discover how these cosmic puzzles have been pondered for centuries, yet continue to reveal new layers of wonder with each passing discovery. So prepare to have your mind expanded and your sense of wonder reignited as we unravel these astonishing alignments that defy explanation and hint at deeper truths about our incredible universe. The journey begins now, and it promises to change how you see everything around you, from the stars above to the very reality we inhabit. Now, consider the sheer improbability of this alignment from a cosmic perspective. The moon's orbit around Earth isn't a perfect circle. It's slightly elliptical, meaning its distance from us varies. At its closest point, the moon appears about 14% larger in the sky, and at its farthest, it appears correspondingly smaller. For a total eclipse to occur, the moon must be near the close part of its orbit at the very same moment it passes directly between Earth and the Sun. This requires a breathtaking synchronization of orbital periods and distances. It's a celestial ballet where every step, every twirl, is timed with impossible precision. This isn't a permanent feature of our solar system either. The moon is slowly drifting away from Earth at a rate of about 1.5 inches every year. Billions of years ago, the moon was much closer and would have completely blotted out the sun's corona, and in the distant future, it will be too far away to fully cover the solar disk, ending the era of total eclipses on Earth. The fact that we exist in this narrow sliver of cosmic time, this perfect window where the alignment is mathematically exact, feels less like a happy accident and more like a ticket to a show that has a very limited engagement. This fleeting perfection has profoundly shaped human history. Ancient civilizations often interpreted eclipses as omens or the anger of gods, events that could topple empires or alter the course of battles. In a more modern context, total solar eclipses have been responsible for monumental scientific breakthroughs. It was during an eclipse in 1919 that observations of starlight bending around the sun confirmed Einstein's theory of general relativity, fundamentally reshaping our understanding of gravity, space, and time. So this cosmic coincidence is far more than a visual spectacle. It's a phenomenon that has ignited both superstition and science, fear and profound discovery, leaving us to wonder if this precise alignment is a random gift of celestial mechanics or a subtle clue pointing toward a deeper, more ordered universe waiting to be understood. But the moon's precise alignment is just the beginning of a much deeper cosmic mystery, one that reaches down into the very fabric of reality itself. If you truly want to be astonished by a number that seems to defy all odds, consider the fine structure constant. This isn't just any number, it's a fundamental value that sits at the heart of physics, approximately 1/137. It governs the strength of the electromagnetic force, the glue that holds atoms together and allows light to interact with matter. What makes this number so utterly baffling to scientists is that it is dimensionless. It doesn't matter what units you use, meters, seconds, kilograms, its value remains the same everywhere in the universe and across all of time. It is a pure, unchanging number that seems to be woven into the cosmos itself. The legendary physicist Richard Feynman called it one of the greatest damn mysteries in physics, a magic number that comes to us with no understanding. He famously said that all good theoretical physicists put this number up on their wall and worry about it. Its precise value is what makes our universe possible. The electromagnetic force is responsible for binding electrons to an atom's nucleus. If the fine structure constant were just a few % larger, electrons would be held so tightly that chemical bonds between atoms could never form. There would be no molecules, no water, no DNA, just a sterile soup of isolated atoms. Conversely, if it were slightly smaller, the electromagnetic force would be too weak to hold onto electrons at all. Atoms would instantly fly apart, and the universe would consist of nothing but a diffuse, lifeless cloud of subatomic particles. This constant directly controls how stars like our Sun produce energy through nuclear fusion. It dictates the specific ways protons can overcome their mutual repulsion to fuse together, creating the light and heat that makes life on Earth possible. Without its exact value, stars would either fail to ignite entirely or would burn through their fuel in a cosmic blink, leaving no time for planets to form or life to evolve. One of the most stunning examples of its fine-tuning is the formation of carbon, the essential element for all known life. Inside stars, carbon is created through an incredibly precise process where 3 helium nuclei come together. The energy levels inside the carbon nucleus have to be exactly right for this triple collision to work, and those energy levels are exquisitely sensitive to the value of the fine structure constant. If that constant were even minutely different, this resonant state would disappear and stars would produce virtually no carbon at all. We simply wouldn't be here. The fact that this number is so perfectly set to allow for carbon-based lifeforms like us to exist and ponder its existence is a coincidence so staggering it has led to intense debate among cosmologists. Some propose the multiverse theory, suggesting our universe is just one of countless others, each with different physical constants, and we naturally find ourselves in the one where the numbers are right for life. Others see it as a potential hint of something deeper, a signature of a universe that isn't just random but is in some profound way meant for discovery. This single number, 1/137th, is a silent architect behind everything we see and are, a whisper of inexplicable order in the apparent chaos of the cosmos. Yet this delicate balance of fundamental forces is only one part of the cosmic recipe for life. For these constants to even matter, they require a stage, a physical place where their perfect values can manifest into a living world. This brings us to our third astonishing coincidence, Earth's ideal distance from the Sun. We exist within a celestial sweet spot known as the habitable zone, or more poetically, the Goldilocks zone. It's not too hot and not too cold, but just right for liquid water to persist on a planet's surface. Our orbit, averaging 93 million miles from the Sun, places us in this narrow, life-giving band. Venture a bit closer, like Venus, and you find a scorching hellscape with surface temperatures hot enough to melt lead, where any water would have boiled away eons ago. Drift a little farther out to the orbit of Mars, and you enter a frozen desert where water exists only as ice, and a thin, wispy atmosphere offers little protection from the cold of space. Earth, by a breathtaking cosmic coincidence, sits perfectly between these two extremes, but the story is far more complex than simple distance. This positioning is not just a matter of orbital real estate, it's the foundation for a symphony of stabilizing factors. Our planet's axial tilt, for instance, is another critical element of this fine-tuning. Tilted at approximately 23.5 degrees, this slight lean gives us our seasons, a gentle, predictable cycling between warmer and cooler periods that helps distribute solar energy across the globe and drives ocean currents and weather patterns that are essential for a diverse biosphere. If Earth had no tilt like Mercury, we would lack seasons entirely, creating stagnant climate bands with a scorching equator and frozen poles. If our tilt were as extreme as Uranus's, which essentially rolls around the Sun on its side, we would experience wildly extreme seasons with parts of the planet plunged into months of continuous darkness or light, making a stable climate nearly impossible. Then there's the Sun itself, a remarkably stable star. Many stars are volatile, unleashing massive flares and violent outbursts of radiation that would regularly sterilize the surfaces of any orbiting planets. Our Sun, however, is a steady, consistent generator of energy. It's in a stable phase of its life cycle, burning hydrogen at a rate that has provided a virtually constant output of warmth for billions of years, giving life the time it needed to emerge and evolve from single-celled organisms into the complex tapestry we see today. This consistent energy is filtered and managed by another crucial component, our atmosphere. Earth's atmospheric composition acts like an intelligent climate control system. It contains just enough greenhouse gases like carbon dioxide and methane to trap sufficient heat to keep the planet from freezing. Yet it doesn't contain so much that it triggers a runaway greenhouse effect, as happened on Venus, which turned that world into a pressure cooker. This atmospheric balance also includes a protective ozone layer that shields the surface from the Sun's most harmful ultraviolet radiation, allowing life to venture onto land. The late astronomer Carl Sagan often marveled at this collection of fortuitous conditions. He described Earth not as a typical planet, but as a rare and precious pale blue dot, a world that has won the cosmic lottery. The odds of a rocky planet forming in just the right place with just the right tilt, orbiting just the right kind of star, and developing just the right atmosphere seem astronomically low. It forces us to confront a profound question. Are we the beneficiaries of an almost unimaginable string of luck, or does our existence in this perfect niche point toward a universe that is, in some fundamental way, predisposed to create life? This exquisite fine-tuning of our planetary home sets the stage for the next incredible coincidence, one that involves a cataclysmic event in our distant past that ultimately made this stable world possible. And yet, the very existence of our perfectly positioned planet, with its life-giving distance from the Sun, hinges on a cataclysmic event of almost unimaginable violence, a cosmic catastrophe that, against all odds, resulted in a blessing. This brings us to our fourth astonishing coincidence, the precise timing and nature of the Moon's formation. The prevailing theory, known as the giant impact hypothesis, paints a dramatic picture of the early solar system, a chaotic shooting gallery where planetary bodies were still colliding and merging. Around 4.5 billion years ago, a nascent Earth, still molten and forming, was struck a glancing blow by a wandering planetary embryo roughly the size of Mars, an object scientists have named Theia. This was not a direct shattering impact but a sideswiper, a collision that occurred at precisely the right angle and at just the right velocity. Had Theia struck head-on, both bodies would have been utterly annihilated, vaporized into a cloud of debris. Had the impact been too shallow, Theia might have simply ricocheted away into space, leaving Earth alone. Instead, this golden impact was a cosmic billiard shot of incredible precision. The collision was violent enough to vaporize a significant portion of Earth's mantle and the entirety of Theia, launching a colossal torus of superheated rock and metal into orbit around our wounded planet. Yet it was gentle enough to leave Earth's core largely intact. From that furious ring of debris governed by gravity, the Moon began to coalesce, cooling and solidifying into the companion we know today. The evidence for this extraordinary event is locked within the Moon itself. Apollo mission astronauts brought back lunar rocks that provided the first crucial clues. The Moon's composition is strikingly similar to Earth's mantle, particularly in its isotopic fingerprints, the unique atomic signatures of elements like oxygen and titanium. This shared heritage strongly suggests the Moon is made primarily from material that once belonged to Earth, not from a completely foreign object. Furthermore, the Moon has a surprisingly small metallic core. This makes perfect sense if Theia's core merged with Earth's during the impact, leaving the ejected material to form a Moon that is relatively iron-poor. Sophisticated computer simulations have modeled this impact scenario thousands of times, and only a very narrow range of angles and speeds produce a Earth-Moon system that looks like the one we have. It was a cosmic roll of the dice that came up exactly right, but the timing of this event is just as crucial as its mechanics. This colossal impact occurred right at the tail end of Earth's primary formation period. It was a final, defining act of planetary birth. The immense energy from the impact effectively melted Earth all over again, allowing heavy elements like iron to sink to the center and complete the formation of our planet's core, which would go on to generate our protective magnetic field. This reset button also helped drive off much of the primitive atmosphere, allowing a new, more stable one to develop later from volcanic outgassing. Perhaps most importantly, the Moon's gravitational influence acts as a steadying hand on Earth's climate. Without our large Moon, Earth's axial tilt would be wildly unstable, wobbling chaotically over millions of years due to gravitational tugs from Jupiter and the other planets. This would lead to extreme and unpredictable climate shifts, turning stability into chaos and making the long, steady evolution of complex life incredibly difficult. The Moon's gravity also provides the gentle brake that has slowed Earth's rotation from a frantic 6-hour day to our 24-hour cycle, creating the daily and tidal rhythms that have influenced the very biology of life on our planet. From a universe-shattering collision came a relationship of perfect harmony, a violent beginning that forged the very stability that life required to eventually flourish. Yet this planetary stability, forged by a violent impact and maintained by our Moon, is not the only layer of cosmic protection we enjoy. Our solar system boasts its own colossal guardian, a gravitational titan whose presence has likely shaped the very history of life on our planet. This brings us to our fifth astonishing coincidence: Jupiter's role as a cosmic shield. As the largest planet in our solar system, a behemoth containing more than twice the mass of all other planets combined, Jupiter exerts a gravitational influence that is nothing short of monumental. Its immense gravity acts like a celestial vacuum cleaner, or perhaps more accurately, a gravitational slingshot, capable of capturing incoming comets and asteroids from the outer solar system, and either pulling them into its own atmosphere or flinging them harmlessly out into interstellar space. This protective effect is thought to have been crucial during the solar system's violent youth, a period known as the Late Heavy Bombardment, when a rain of debris pummeled the inner planets. By clearing out a significant portion of this primordial debris, Jupiter may have created a safer, more stable environment in which Earth could finish forming and eventually give rise to life. The concept of Jupiter as a protector was first popularized by the work of astronomer George Wetherill in the 1990s. His simulations suggested that without a giant planet in a Jupiter-like orbit, the impact rate on Earth would be 1,000 times greater, subjecting our world to a continuous, sterilizing barrage of extinction-level events. In this light, our gas giant appears as a benevolent guardian, a gravitational buffer that has significantly reduced the number of catastrophic collisions over billions of years. A stunning real-world demonstration of this protective power occurred in July 1994, when astronomers watched in awe as fragments of the comet Shoemaker-Levy 9, which had been torn apart by Jupiter's gravity on a previous pass, slammed into the planet's southern hemisphere. The impacts created massive, Earth-sized plumes of fire and dark scars in Jupiter's atmosphere that persisted for months. This event was a dramatic live-action replay of the kind of catastrophe that Jupiter has likely taken on our behalf countless times throughout history. It was a visceral reminder that the solar system is still a dynamic and sometimes dangerous place, and that we have a powerful neighbor intercepting threats. However, the story is not entirely clear-cut, and some planetary scientists argue that Jupiter's role is more complex than that of a simple guardian. Its tremendous gravity can sometimes perturb the orbits of objects in the asteroid belt, potentially sending them on new trajectories that cross Earth's path. In this view, Jupiter might also act as a source of danger, a gravitational agitator that occasionally kicks rocks inward toward us. This dual nature adds a fascinating layer of nuance to the coincidence. It suggests that Jupiter's influence is not purely protective, but that its net effect over the vast stretches of geological time has been to create a more stable and less chaotic impact environment for Earth. The precise balance of these effects, how many objects it flings away versus how many it sends our way, appears to be exquisitely fine-tuned. If Jupiter were significantly more massive or occupied a different orbit, its disruptive influence might dominate, turning it into a malevolent disruptor rather than a shield. The fact that it exists in its current mass and position, providing a net protective benefit, is yet another roll of the cosmic dice that came up in our favor. This leads to a profound and humbling reflection. The long, relatively peaceful intervals between mass extinction events on Earth, which have allowed intelligent life the time to evolve and civilizations to develop, might not be solely due to our planet's own qualities. They could be, in part, a gift from a giant world hundreds of millions of miles away. Our existence may be intertwined with the gravitational dynamics of our entire solar system, a delicate dance where the placement of the largest player has helped to choreograph a safer stage for life to perform its slow, beautiful evolution. It forces us to broaden our perspective from our own planet to the architecture of our entire cosmic neighborhood, and to wonder if such a protective arrangement is common around other stars, or if we, once again, have won a celestial lottery. This external safeguarding, however, would mean little without the intricate, life-preserving systems operating right here at home, beginning with the very air we breathe. While Jupiter's immense gravity shields us from external cosmic threats, our planet's own internal systems have crafted a different kind of shield, one that is just as vital and even more delicate, the very air we breathe. This brings us to our sixth astonishing cosmic coincidence, the precise and stable balance of oxygen in Earth's atmosphere. For us, taking a breath is a simple, unconscious act, but that single breath contains a miracle of planetary engineering. Our atmosphere is composed of roughly 21% oxygen, a percentage that represents a breathtakingly narrow window for possibility. If that level were to drop significantly, even just a few percent, complex animal life would struggle to survive, suffocating under the weight of its own metabolic needs. Aerobic organisms, including ourselves, rely on that specific concentration to efficiently fuel our cells and power our brains, but the danger exists on the other side as well. If the oxygen level were to rise much higher, say to 25 or 30%, the entire planet would become a tinderbox. Wet vegetation, which normally resists burning, would dry out and become highly flammable. A single lightning strike could ignite continental-scale wildfires, ripping across landscapes with terrifying speed and ferocity. Beyond the fire risk, higher oxygen levels become toxic, causing damage to lung tissue and cellular structures. So we exist on a razor's edge, in an atmosphere that is both life-giving and life-limiting, a perfect equilibrium that has been maintained for millions of years against all odds. This stability is not a happy accident. It is the result of an immensely complex and dynamic planetary scale dance between biology and geology. The primary engine for this balance is, of course, photosynthesis. For billions of years, plants, algae, and cyanobacteria have been consuming carbon dioxide and releasing oxygen as a waste product, slowly transforming the primitive, toxic atmosphere of early Earth into the breathable air we enjoy today. But if this were a one-way process, oxygen levels would have skyrocketed long ago, leading to the catastrophic scenarios we just imagined. This is where the other half of the cycle comes into play. Respiration and decomposition act as a counterbalance. Animals and microbes consume oxygen and release carbon dioxide, effectively recycling the atmospheric ingredients. Furthermore, geological processes play a crucial role. The weathering of silicate rocks on land pulls carbon dioxide out of the atmosphere, which indirectly helps regulate oxygen over vast stretches of time. Even the burial of organic carbon, the remains of plants and creatures that escape decomposition, is a critical factor. When this carbon is buried in sediments on the ocean floor, it effectively locks away the carbon that would have otherwise combined with oxygen, allowing oxygen levels to remain stable. It is a self-regulating feedback loop of incredible elegance and complexity. This idea of a self-regulating planet is central to the Gaia hypothesis proposed by scientist James Lovelock. He suggested that life itself actively manages and maintains the conditions necessary for its own survival, turning the entire biosphere into a single, vast, living system. The oxygen balance is a prime example of this. The biosphere doesn't just exist within its environment. It constantly shapes and stabilizes that environment, creating a haven for complexity against the entropic tendencies of the universe. We can see what happens when this balance is lost by looking at our neighboring worlds. Venus possesses a crushing atmosphere of 96% carbon dioxide, a runaway greenhouse effect that has boiled its surface. Mars has a thin, wispy atmosphere that is also mostly carbon dioxide, but it's so thin it cannot retain heat or protect the surface from radiation. Neither offers the stable, mixed, and life-giving atmosphere that Earth enjoys. Even our own planet's history shows us the fragility of this balance. Around 2.4 billion years ago, the Great Oxidation Event was a planetary crisis. As cyanobacteria began pumping oxygen into the atmosphere for the first time, it was a poison to the ancient anaerobic life that dominated the planet, causing a mass extinction. It also rusted the oceans, pulling iron out of the water and forming massive banded iron formations that we now mine for steel. This event proves that atmospheric equilibrium is hard-won and can be violently disrupted. Today, a new force is actively testing this delicate balance of human activity. The burning of fossil fuels, which is essentially the rapid unburial of that ancient carbon, and massive deforestation, are significantly altering the intricate cycles that have maintained our atmosphere for eons. We are adding carbon dioxide at an unprecedented rate, while SIMULT at NEOUSLY Chinese letter ING, the planet's ability to reabsorb it through the loss of forests and phytoplankton blooms. While the immediate concern is global warming due to CO2, this massive perturbation of Earth's carbon cycle could, over time, have unforeseen consequences for our planet's oxygen regulation systems. It is a stark reminder that this 21% oxygen level is not a guaranteed constant. It is a dynamic and fragile achievement, the result of billions of years of planetary evolution and biological collaboration. The fact that this precise balance exists at all and has persisted long enough for intelligent life to evolve and ponder its existence is a coincidence of cosmic proportions. It suggests a universe capable of not only creating the right physical constants and planetary positions, but also of fostering the intricate, self-sustaining systems that turn a mere rock into a living, breathing world. This invisible shield of air, perfectly composed and maintained, is perhaps the most intimate and vital of all our cosmic coincidences, a daily reminder that we are living within a masterpiece of planetary art. But the story of our atmosphere is just one chapter in a far grander tale of cosmic fine-tuning, a narrative that stretches all the way back to the very beginning of everything. To uncover our next coincidence, we must journey back in time, not just millions, but over 13 billion years to the universe's very first light. This brings us to the seventh astonishing cosmic coincidence, the breathtaking uniformity of the cosmic microwave background radiation. Think of this as the universe's baby picture, the faded afterglow of the Big Bang itself, a faint whisper of heat that permeates all of space. When scientists first pointed their instruments at this primordial glow, they expected to find a sky filled with dramatic temperature variations, the cosmic seeds from which galaxies and vast clusters would eventually grow. Instead, they found something that defied all expectation, a background of stunning, almost unbelievable smoothness. No matter which direction they looked, the temperature of this radiation was the same to within 1 part in 100,000. To put that incredible precision into perspective, that's like comparing the smoothness of a billiard ball to the roughness of our entire planet Earth. This level of uniformity is a profound puzzle because the early universe, as we understand it, simply didn't have enough time to mix and smooth itself out to this degree. This discovery, first made with exquisite detail by satellites like the Cosmic Background Explorer, or COBE, and later refined by the Planck mission, presented cosmologists with a monumental challenge known as the Horizon Problem. In the standard Big Bang model, two opposite sides of the observable universe were never in contact with each other. They were separated by distances so vast that not even light, the universe's ultimate speed limit, could have traveled between them to exchange energy and heat and create this uniform temperature. It would be like walking into two identical bakeries on opposite sides of the world and finding that every single loaf of bread was baked at exactly the same temperature to within 1,000th of a degree, even though the bakers had never spoken or shared a recipe. This seemingly impossible level of coordination demanded a radical new explanation. The solution, proposed by physicist Alan Guth, is known as cosmic inflation. This theory suggests that in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of hyper-exponential expansion, inflating from a subatomic speck to something approaching the size of a grapefruit faster than the speed of light. This incredible burst of growth would have stretched any initial irregularities smooth, ironing out the wrinkles in spacetime itself and creating the phenomenal uniformity we observe in the cosmic microwave background. It set the stage for everything that was to follow. Yet for all its explanatory power, inflation theory itself introduces a new layer of mystery. While it elegantly solves the horizon problem, the exact mechanism that triggered this inflationary epoch, and just as importantly, what stopped it, remains one of the biggest unsolved problems in physics. The driving force behind inflation is thought to be a mysterious energy field called the inflaton, but we have no direct evidence for its existence or its properties. This leads to a fascinating and almost philosophical dilemma. Was this period of inflation a natural, albeit poorly understood, physical process? Or does the fact that it happened with just the right characteristics to create a universe capable of supporting life point toward something more deliberate? The minuscule fluctuations that inflation did leave behind, those 1 part in 100,000 variations, are themselves a form of cosmic fine-tuning. These tiny ripples in density are the gravitational seeds from which all cosmic structure sprang. They were exactly the right size. If they had been significantly smaller, gravity would never have been strong enough to pull matter together to form galaxies, stars, and planets. We would live in a vast, dark, and utterly empty cosmos. If the fluctuations had been much larger, matter would have collapsed into a swarm of enormous, primordial black holes long before stars could ever form, creating a universe equally hostile to life. The cosmic microwave background, therefore, is not just a perfectly smooth canvas. It is a canvas with the perfectly imperfect brushstrokes needed to create a grand and beautiful cosmic painting. This ancient light does more than just tell us about the universe's infancy. It also acts as a powerful probe into its deepest secrets, shaping our understanding of its composition and ultimate fate. The precise pattern of hot and cold spots in the CMB is a rich source of data, a cosmic code that reveals the universe's total density, its geometry, and the nature of its most mysterious components, dark matter and dark energy. The patterns are consistent with a universe that is geometrically flat, a critical balance we will explore in a later coincidence, and they confirm that dark matter, an invisible form of matter that interacts only through gravity, must exist in far greater quantities than the ordinary atoms that make up our world. It was the gravitational pull of this dark matter that provided the scaffolding upon which the first galaxies could form, gathering the primordial hydrogen gas around it. Without it, the universe would lack the large-scale structure we see today. The CMB also provides our earliest clean measurement of dark energy, the enigmatic force that would later come to dominate the universe and accelerate its expansion. So this faint, cold glow is far more than a relic. It is a foundational blueprint. It is the universe's opening chord, a note of incredible harmony struck at the moment of creation, whose resonance determined the entire symphony of cosmic evolution that followed. Its paradoxical combination of overwhelming uniformity and exquisitely tuned imperfection stands as one of the most compelling pieces of evidence that our universe is built on a foundation of astonishing and perhaps intentional precision. Just as the cosmic microwave background revealed a universe of stunning smoothness, a more recent and equally shocking discovery turned our understanding of the cosmos on its head, leading us to the eighth astonishing cosmic coincidence, the accelerating expansion of the universe driven by dark energy. For most of the 20th century, astronomers were locked in a debate about the ultimate fate of everything. Would the collective gravity of all the matter in the universe eventually slow its expansion from the Big Bang to a halt, leading to a big crunch where everything collapses back in on itself? Or would the expansion continue forever, gradually slowing down but never stopping, leading to a cold, dark, and lonely heat death? The answer, when it finally came, was something nobody had seriously predicted. In the late 1990s, two independent teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic mile markers to measure how the expansion rate had changed over billions of years. They expected to find that the expansion was slowing down. Instead, their data told a story that was both baffling and revolutionary. The expansion of the universe wasn't slowing down at all, it was speeding up. Some mysterious, repulsive force was acting against gravity, pushing galaxies apart at an ever-increasing rate. This discovery was so profound and unexpected that it earned team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. This mysterious force was dubbed dark energy, and its nature remains one of the greatest unsolved puzzles in all of science. Measurements from supernova, combined with data from the cosmic microwave background and galaxy surveys, have since revealed that dark energy makes up a staggering 68% of the total energy density of the universe. To put that into perspective, the ordinary atoms that make up everything we can see, stars, planets, and people, account for less than 5%. Dark matter, the invisible gravitational scaffolding for galaxies, makes up about 27%. Dark energy is the dominant component of the cosmos, the primary driver of its ultimate fate, and we have almost no idea what it actually is. The leading candidate is Einstein's cosmological constant, a term he originally inserted into his equations of general relativity to describe a static universe and later called his biggest blunder. This concept posits that dark energy is an inherent property of the vacuum of space itself, a constant energy density that doesn't dilute as the universe expands. As more space comes into existence, more of this repulsive energy appears, leading to a runaway acceleration. Other theories propose that dark energy is not constant but a dynamic force field, sometimes called quintessence, which could vary over time and across space. Yet, despite decades of searching, no definitive evidence has been found to distinguish between these ideas. What makes dark energy a true cosmic coincidence is its inexplicably small but perfectly balanced value. The energy density of empty space, as measured by astronomers, is around 120 orders of magnitude smaller than what quantum field theory predicts it should be. This is not a small discrepancy, it is the worst prediction in the entire history of physics. If the theoretical value were correct, the repulsive force of this vacuum energy would have been so unimaginably powerful in the instant after the Big Bang that it would have ripped apart every proton and neutron before they could even form, preventing the existence of atoms, stars, or galaxies. Our universe would have been stillborn. For a universe to be habitable, the value of dark energy must be incredibly tiny, almost but not quite zero, and that is precisely what we observe. Its strength appears to be exquisitely fine-tuned. If dark energy were significantly stronger, its repulsive force would have dominated much earlier in cosmic history. It would have prevented matter from ever clumping together under gravity, tearing apart the primordial clouds of gas before they could collapse into the first galaxies. The cosmos would be a vast, empty, and expanding void with no structure whatsoever. Conversely, if dark energy were slightly weaker, or even attractive like gravity, the universe would have recollapsed into a big crunch billions of years ago, long before stars could forge the heavy elements necessary for life or planets could form stable environments. There would have been no time for evolution to produce beings capable of pondering the universe's mysteries. This perfect balance has led some scientists to consider the anthropic principle, the idea that the fundamental constants of nature must be compatible with the existence of observers. In this view, we find ourselves in a universe with a specific, life-allowing value for dark energy simply because we are here to observe it. This line of reasoning often leads to the controversial multiverse hypothesis, which suggests our universe is just one bubble in a vast cosmic foam of universes, each with different physical constants and laws. In most of these universes, the value of dark energy is wrong and life never arises. We, by necessity, exist in one of the rare universes where the numbers are just right. Whether one finds this explanation satisfying or not, the undeniable fact is that the strength of dark energy is a parameter that had to be set with impossible precision for our existence to be possible. It is a silent, invisible, and dominant force that has been shaping the cosmos since its earliest moments, and its value is a non-negotiable requirement for a universe that can contain galaxies, stars, planets, and life. This profound fine-tuning of the universe's expansion rate forces us to confront the possibility that the laws of physics are not just a set of arbitrary rules, but may themselves be the product of a deeper, more fundamental order, an order that we are only just beginning to glimpse. From the vast, accelerating expanse governed by dark energy, we now plunge into the incredibly small, to a ghostly particle that barely interacts with the world yet has profoundly shaped it. This brings us to our ninth astonishing cosmic coincidence, the enigmatic, precisely tuned mass of the neutrino. For decades, the standard model of particle physics held that these elusive particles were completely massless, zipping through the cosmos at the speed of light and barely interacting with ordinary matter. They are the cosmic phantoms, so ethereal that trillions of them pass through your body every second without a single trace, remnants from the Big Bang and the nuclear furnaces of stars. But in the late 1990s, a monumental discovery at the Super Kamiok and Observatory in Japan shattered that long-held belief. This enormous detector, a massive tank filled with 50,000 tons of ultra-pure water buried deep beneath a mountain, provided irrefutable evidence that neutrinos do, in fact, possess mass. They oscillate, changing from one type electron, muon or tau, to another as they travel, a quantum metamorphosis that is only possible if they have mass. This discovery was so groundbreaking that it earned physicist Arthur MacDonald a share of the Nobel Prize, fundamentally rewriting the textbooks and revealing a new layer of subtlety in the laws of physics. But here's where the coincidence becomes truly mind-bending. The mass that neutrinos do have is almost inconceivably small. They are billions of times lighter than the electron, the next lightest particle. To put it in perspective, if an electron were the size of a penny, a neutrino would have a mass smaller than a single grain of dust. This isn't just a small number, it is a number that exists in a breathtakingly narrow sweet spot with cosmic consequences. Neutrinos were produced in unimaginable numbers during the Big Bang, and they still flood the universe today. If they were completely massless, as once thought, their incredible speed would have prevented them from clumping together under gravity. They would have had no meaningful effect on the formation of the large-scale structure of the universe, the web of galaxies and galaxy clusters that defines the cosmos. On the other hand, if neutrinos had even a modest amount of mass comparable to that of an electron, the story would be terrifyingly different. Their sheer abundance would have provided so much extra gravitational pull that the universe would have collapsed back on itself in a big crunch eons ago, long before any stars could form. Their mass had to be tiny, but not zero. This exquisitely small mass allows neutrinos to play a unique and vital role in cosmic evolution. In the early universe, these lightweight particles streamed freely out of dense regions, carrying energy away with them. This process actually helped to smooth out the tiny density fluctuations we see in the cosmic microwave background, preventing the smallest clumps of dark matter from growing too quickly. By acting as a subtle damping force, neutrinos help determine the minimum size for the first galaxies. They essentially set a cosmic filter, ensuring that only the largest and most stable gravitational wells could form the first stars and galaxies, creating a universe with a balanced mix of colossal galaxy clusters and smaller dwarf galaxies. Without this neutrino filtering effect, the cosmos might be a chaotic mess of tiny, unstable star systems, or conversely, a few monstrously large megagalaxies, neither of which would be particularly conducive to the formation of stable, life-friendly solar systems like our own. The fine-tuning of the neutrino's mass extends beyond galaxy formation and into the very elements that make up our bodies. Their role is critical in the violent death of massive stars in supernova explosions. When a star's core collapses, 99% of the enormous energy released is carried away not by light, but by a tremendous blast of neutrinos. This neutrino burst is the driving engine of the explosion itself, responsible for blasting the star's outer layers, enriched with newly forged heavy elements like carbon, oxygen, and iron, out into the interstellar medium. The precise mass and properties of neutrinos govern the efficiency of this process. If their mass were different, this explosive transfer of energy could fail. The supernova could fizzle, collapsing directly into a black hole without releasing its precious cargo of life-essential elements into the galaxy. We are quite literally made of stardust, and the process that scattered that dust across the cosmos was delicately orchestrated by the properties of these ghostly particles. Furthermore, the fact that neutrinos have mass might be a crucial clue in solving one of the universe's greatest mysteries: why there is any matter left at all. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind a universe of pure energy. The slight asymmetry that favored matter might be linked to how neutrinos oscillate and how they interact with their own antiparticles, a process that relies on them having mass. So we are left with a profound question. Why does a particle so insignificant in weight wield such cosmic influence? The fact that its mass is not zero, but is instead placed in a perfect Goldilocks zone that allows for galaxy formation, stellar explosions, and potentially the existence of matter itself, feels less like a random outcome and more like a fundamental parameter set with breathtaking precision. It is a whisper from the quantum realm that echoes across the breadth of the universe, a subtle tuning that once again makes our existence possible. The neutrino teaches us that significance is not always measured in size or strength, but sometimes in the delicate, almost imperceptible balance of forces that allow a universe to build itself into something complex and beautiful. This exploration of a particle that defies easy categorization naturally leads us to consider the overall shape and geometry of the cosmos itself, and another coincidence written on the largest possible scale. From the ghostly subtlety of neutrino masses, we now expand our view to the grandest scale imaginable: the overall shape and geometry of the entire cosmos. This brings us to our 10th astonishing cosmic coincidence: the near-perfect flatness of the universe. In the context of cosmology, flatness doesn't refer to a two-dimensional pancake. Instead, it describes the geometry of spacetime itself on the largest scales. According to Einstein's theory of general relativity, the universe can take one of three possible shapes: dictated by the total amount of matter and energy it contains. It could be positively curved like the surface of a sphere, where parallel lines eventually meet and the angles of a triangle add up to more than 180 degrees. It could be negatively curved like a saddle, where parallel lines diverge and triangle angles sum to less than 180 degrees. Or it could be perfectly flat, where the familiar rules of Euclidean geometry hold true and parallel lines remain parallel forever. For a universe to be flat, its total density must be exactly at the critical density, a precise balance between the expansive force of the Big Bang and the contractive pull of gravity. The truly staggering fact is that our universe is measured to be flat to within an accuracy of 1 part in 100,000. This incredible precision was not always assumed. For much of the 20th century, astronomers debated which of the 3 geometries described our cosmos. The answer came from multiple, independent lines of evidence, all converging on the same flat conclusion. The most powerful data comes from the detailed maps of the cosmic microwave background. The apparent size of the hot and cold spots in this primordial light acts as a cosmic ruler. In a positively curved spherical universe, these spots would appear larger to us. In a negatively curved, saddle-shaped universe, they would appear smaller. The Planck satellite and other observatories have measured these spots with exquisite detail, and their size is exactly what is predicted for a universe with zero curvature, a perfectly flat geometry. This is further confirmed by observations of the large-scale structure of the universe, the vast cosmic web of galaxies and galaxy clusters, which also aligns perfectly with a flat model. The problem, and the reason this is a profound coincidence, is that a flat universe is incredibly unstable. Think of it like balancing a pencil perfectly on its point. The tiniest nudge in any direction will cause it to fall over. In the same way, for the universe to remain flat over billions of years, its density at the very beginning had to be fine-tuned to an unimaginable degree. If the density at 1 second after the Big Bang had been even the slightest bit higher than the critical value by just 1 part in 10 to the power of 60, the universe would have quickly collapsed back in on itself in a big crunch, lasting only a fraction of a second. If the density had been the same minuscule amount lower, the universe would have expanded so rapidly that matter would have flown apart before gravity could pull it together to form even the simplest atoms, let alone stars and galaxies. We exist because an impossible balance was struck at the moment of creation. The leading theory to explain this miraculous flatness is once again cosmic inflation. That brief period of hyper-expansion would have stretched the fabric of space-time so dramatically that it would have forced the universe's curvature toward zero, just as inflating a balloon makes any small section of its surface appear flatter and flatter. Inflation provides a mechanism to achieve flatness, but it doesn't fully erase the mystery. It simply pushes it back a step. It requires its own set of exquisitely fine-tuned initial conditions to begin and end at just the right moment to produce the flat universe we observe. The fact that we live in a universe that is not just approximately flat, but flat to a precision of 1 part in 100,000, is a testament to a level of geometric perfection that defies simple chance. This flatness is not a mere curiosity. It is a fundamental prerequisite for a long-lived, structured, and habitable cosmos. It provides the stable stage upon which the 13.8 billion-year drama of galaxy formation, stellar evolution, and the emergence of life could unfold. This perfect geometric balance forces us to confront the possibility that the underlying architecture of our reality was crafted with a precision that borders on the miraculous, setting the stage for the next chapter in our cosmic story, the remarkable timing of our own appearance on this stage. This breathtakingly precise cosmic geometry, a stage set with perfect flatness for billions of years, raises a question of profound personal significance. Why are we here to observe it now? This brings us to our 11th astonishing cosmic coincidence, the incredibly fortuitous timing of human evolution. We, a species capable of building telescopes and unraveling the secrets of the cosmos, have emerged at what appears to be a very special moment in the entire 14 billion-year history of the universe, a narrow window of cosmic quiet that has allowed us to not only exist but to look back and understand our origins. Consider the sheer expanse of time. For the vast majority of the universe's existence, conditions were utterly hostile to any form of complex life. The first several hundred million years after the Big Bang, known as the Cosmic Dark Ages, were a time when space was filled with a hot, opaque fog of ionized gas. No stars or galaxies had yet formed. There was nothing to see, and certainly no one to see it. Even after the first stars ignited, their violent lives and explosive deaths filled the cosmos with sterilizing radiation. It took generations of stars living and dying to forge and scatter the heavy elements, the carbon, nitrogen, oxygen, and iron, that are the essential building blocks of planets and life itself. Our solar system and our very bodies are made from this stardust, the ashes of long-dead stars. We could not have existed any earlier because the universe had not yet finished cooking the ingredients necessary for our formation. But it's not just about having the right materials, it's also about finding a safe and stable neighborhood. Our sun is a remarkably stable, middle-aged star, reliably fusing hydrogen into helium in its core. This main sequence phase provides Earth with a constant source of energy for billions of years, a longevity that is absolutely essential for the slow, gradual process of evolution to take single-celled organisms and sculpt them into intelligent, technological beings. Stars much more massive than the Sun burn far too brightly and die in spectacular supernova after only a few million years, snuffing out any chance for life on nearby planets to advance beyond its most primitive stages. Furthermore, the chaotic early days of our solar system, a period of frequent and catastrophic asteroid impacts known as the Late Heavy Bombardment, had to subside. The massive shock of an asteroid impact can reset the evolutionary clock, as it likely did when a 6-mile-wide rock struck Earth 66 million years ago, ending the reign of the dinosaurs and clearing the ecological stage for mammals to eventually rise. Had such an event occurred much later in our own evolutionary history, it could have easily wiped out our early hominid ancestors. We exist during a period of unusual planetary calm, a ceasefire in the celestial shooting gallery that has prevailed for the last several hundred million years. This collection of fortunate timing is at the heart of what philosophers and scientists call the anthropic principle. In its simplest form, it states that the universe must have the properties it does because we are here to observe them. If the constants of nature or the timeline of cosmic history were even slightly different, we simply wouldn't be around to ponder the question. Think of Brandon Carter, who coined the term, highlighted that we should not be surprised to find ourselves living at a time when the universe is still transparent and its mysteries are accessible. In the far, far future, trillions of years from now, the accelerating expansion driven by dark energy will have pushed all other galaxies beyond our observable horizon. The night sky for any future civilizations will be utterly black and empty, devoid of any evidence for the Big Bang or an expanding universe. The cosmic microwave background radiation will have redshifted into undetectability, its faint whisper lost forever. Those future observers, if they exist, would have no clue about the true nature, history, or grand scale of the cosmos they inhabit. Their science would be built on a fundamentally incomplete and local picture of reality. We, by contrast, live in a privileged era of observation, a golden age of astronomy where we can still see the afterglow of creation and trace the outlines of the cosmic web. Our timing is impeccable, so does this mean our emergence was inevitable, a preordained outcome of a universe fine-tuned for life? Or are we the beneficiaries of an almost endless series of lucky breaks, a statistical fluke in a cosmos that is largely indifferent? The evidence suggests a middle path. The universe provides the potential for life through its precise laws and constants, but the actual emergence of intelligence seems to require a long and fragile chain of events, each dependent on the last. We are not at the center of the universe in a geographic sense, but we may well be at a central point in time for the act of cosmic observation. This places upon us a unique responsibility and a profound sense of wonder. We are the universe becoming aware of itself at the one moment in its entire lifespan when such awareness is possible. This temporal alignment, this perfect storm of stability, safety, and accessibility, is one of the most deeply personal and humbling of all the cosmic coincidences, connecting our own brief story directly to the grandest narrative of all. While we exist within the safe harbor of our solar system's delicate balances, our entire cosmic neighborhood is itself on a grand journey, orbiting the heart of our galaxy. This brings us to our 12th astonishing cosmic coincidence, our solar system's privileged alignment within the Milky Way, a specific location that places us in a life-friendly corridor known as the Galactic Habitable Zone. Our planet doesn't just orbit a stable star. Our entire star system is perfectly positioned within the galaxy itself, avoiding the most dangerous regions and cruising through a relatively quiet spiral arm that offers a remarkable combination of safety and resources. We are located about 27,000 light-years from the chaotic galactic center, nestled within the Orion Cygnus arm, a minor spiral arm of the Milky Way. This specific address is far from arbitrary. It represents a sweet spot that appears to be crucial for the development and long-term survival of complex life. To understand why this location is so special, we need to consider the alternative. The central bulge of the Milky Way, like most galaxies, is an incredibly violent and energetic place. It is densely packed with stars, often separated by mere light weeks instead of light years. In such a crowded environment, gravitational interactions would be constant and catastrophic, easily pulling planets from their stable orbits around their parent stars and flinging them into the cold depths of interstellar space or into fiery collisions. Even more dangerous is the supermassive black hole that lurks at the very center of our galaxy, Sagittarius, a star. While currently quiet, this behemoth, with a mass 4 million times that of our Sun, can periodically become active, consuming nearby material and unleashing unimaginable blasts of X-rays and gamma rays that would sterilize any planetary system within tens of thousands of light-years. The inner galaxy is also a frequent site of supernova explosions, the violent deaths of massive stars. A nearby supernova within just a few dozen light-years would bathe a planet in lethal radiation, stripping away its atmosphere and scorching its surface. Our position, far from this crowded and explosive downtown, provides a vital buffer against these existential threats. However, we are not so far out in the galactic suburbs that we are completely isolated. The very outer reaches of a galaxy are known as the galactic halo, a sparse region where stars are few and far between. While safe from supernova and black holes, a planet in this region would suffer from a different problem, a poverty of elements. The heavy elements necessary to form rocky planets like Earth, iron, silicon, oxygen, and carbon are forged in the hearts of stars and scattered throughout the galaxy by supernova explosions. These elements are much more concentrated in the galactic disk, particularly in the spiral arms. Our position in the Orion arm represents a perfect compromise. We are far enough from the center to avoid its dangers, but we are still within the rich, chemically enriched disk of the galaxy, ensuring that our solar system formed from a nebula abundant with the heavy elements required for terrestrial planets and ultimately for life itself. Our journey through the galaxy is not a simple circular orbit. It also has a vertical component, bobbing up and down through the galactic plane as we go around. This motion, too, seems finely tuned. Our solar system's path keeps us within the thin disk of the galaxy, where the density of interstellar gas and dust is low. If our orbit took us repeatedly through the thicker parts of the galactic plane, we would encounter denser clouds of material. These clouds could gravitationally perturb the vast reservoir of comets in the distant Oort cloud, sending a shower of icy bodies hurtling into the inner solar system and dramatically increasing the rate of comet impacts on Earth, leading to potential extinction events. Our current, relatively stable vertical oscillation helps to minimize these disturbances, contributing to the long-term climate stability that has allowed life to evolve over billions of years. Astronomers like Guillermo Gonzalez, who pioneered the concept of the galactic habitable zone, argue that this combination of factors, the right distance from the center, the right chemical enrichment, and the right orbital dynamics creates a narrow ring within a galaxy where life has the best chance to arise and persist. It appears that we don't just live in a friendly solar system, we live in a friendly neighborhood within a friendly galaxy, a series of nested safe havens that have collectively nurtured our existence. This realization that our address is fine-tuned on a galactic scale profoundly expands the scope of the cosmic coincidences we must consider, pushing our gaze from the physics of atoms to the architecture of the universe itself. Yet for all the protection offered by our galactic neighborhood, the very existence of the atoms that make up our world, our galaxy, and even ourselves hinges on a fundamental and deeply mysterious imbalance written into the laws of physics at the very instant of creation. This brings us to our 13th astonishing cosmic coincidence, the profound and unexplained asymmetry between matter and antimatter. According to our best theories of particle physics, the Big Bang should have been a perfectly symmetrical event, producing equal amounts of matter and its mirror opposite, antimatter. For every quark of matter created, an antiquark should have been created alongside it. The same goes for electrons and positrons and all other particle pairs. And herein lies the problem. When a particle of matter meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the universe had begun in a state of perfect symmetry, all the matter and all the antimatter would have completely obliterated each other within the first second of existence. The cosmos would be nothing but a vast, expanding sea of featureless radiation, no atoms, no stars, no planets, and certainly no one to wonder about it. Yet here we are in a universe filled with galaxies, stars, and planets, all made exclusively of matter. This means that for some reason, this perfect symmetry was broken. Out of every billion pairs of matter and antimatter particles that were created and annihilated in the Big Bang, a tiny surplus of just one matter particle was left over. That one in a billion imbalance is all there is. Every single atom in the observable universe, from the hydrogen in distant nebulae to the carbon in our own bodies, is a relic of that unimaginably small excess. We are the leftover crumbs from a near-total annihilation. This mystery, known as Baryon asymmetry, is one of the most significant open questions in all of cosmology. The great Soviet physicist and dissident Andrei Sakharov was the first to outline the three necessary conditions that must be met for such an imbalance to occur. First, there must be a process that violates the conservation of baryon number, meaning the total number of matter particles is not strictly constant. Second, the fundamental symmetries of charge and parity must be violated, meaning the laws of physics must treat particles and their mirror image antiparticles slightly differently. And third, these processes must occur out of thermal equilibrium, meaning they happen when the universe is rapidly expanding and cooling, preventing the system from simply readjusting back to symmetry. While physicists have discovered phenomena that satisfy some of Sakharov's conditions, for instance, certain particle decays do exhibit violations of charge and parity symmetry, the complete picture remains elusive. The effects we have measured in laboratories are far too small to account for the vast surplus of matter we see in the cosmos. They can only produce a tiny fraction of the 1 part in a billion imbalance we require. This suggests that the true source of the asymmetry must lie in new physics, in processes that occurred at energy scales far higher than we can currently probe with our particle accelerators. This is where massive experiments like the Large Hadron Collider at CERN come into play. Scientists are meticulously studying the behavior of quarks and other fundamental particles, searching for any additional, larger violations of the symmetry laws that govern matter and antimatter. They are looking for clues in the subtle differences between how particles and antiparticles decay, hoping to find a smoking gun that points toward a more powerful mechanism that operated in the infant universe. Some theories point to extremely heavy, as yet undiscovered particles that existed only in the first moments after the Big Bang. As these particles decayed out of equilibrium, they could have preferentially produced more matter than antimatter, seeding the universe with the initial surplus we see today. Other ideas involve processes that occurred during the inflationary epoch or even more exotic concepts. The search is a painstaking process of elimination and discovery, a cosmic detective story trying to explain our very existence. The profundity of this coincidence cannot be overstated. The fate of the entire universe, whether it would be a lifeless void or a vibrant tapestry of structure, was decided by a deviation so minuscule it defies comprehension. It is a statistical fluke of cosmic proportions. This leads to a deeply philosophical question. Why does anything exist at all? The fact that there was any imbalance, however small, seems to go against the most fundamental expectations of symmetry and economy in physical law. It feels less like an accident and more like a prerequisite. Was this asymmetry simply a random quantum fluctuation frozen into the fabric of the expanding cosmos? Or does it point toward a deeper layer of physical law, a fundamental lopsidedness in the universe that prefers existence over nothingness? The fact that this 1 in a billion imbalance was precisely what was needed to eventually form hundreds of billions of galaxies, each containing billions of stars and planets, suggests a level of fine-tuning that is as breathtaking as it is inexplicable. This primordial preference for matter is the ultimate foundation for everything we hold familiar, the silent reason there is a universe of stuff to study instead of a universe of empty light. While the ghostly neutrino and the matter-antimatter imbalance operate on a subatomic scale, the very structure of the atoms that make up our world relies on a force of immense power and breathtaking precision. This brings us to our 14th astonishing cosmic coincidence, the perfectly calibrated strength of the strong nuclear force. Imagine trying to build a universe. You have your ingredients, positively charged protons and neutral neutrons, but there's a problem. Protons, all carrying the same positive charge, violently repel each other due to the electromagnetic force. If that were the only force at play, atomic nuclei could never form. The repulsion would instantly blast them apart. Yet we are surrounded by stable matter, from the air we breathe to the planets we orbit. This is only possible because of the strong nuclear force, the most powerful fundamental force in nature, but one that operates over an incredibly short range. It acts as the ultimate cosmic glue, binding protons and neutrons together into atomic nuclei, overcoming their fierce electromagnetic repulsion to create the stunning diversity of elements that form the periodic table. The truly remarkable thing about this force is not its raw strength, but its exquisitely fine-tuned value. The strength of the strong force is set within a vanishingly narrow window that allows for the existence of a rich array of stable elements, which are the absolute prerequisite for chemistry, planets, and life. If the strong force were even slightly weaker, it would be unable to overcome the repulsive force between protons. The only stable nucleus would be hydrogen, a single proton. No other elements could form. There would be no carbon, no oxygen, no nitrogen, no building blocks for planets or living organisms. The universe would be a boring, featureless sea of hydrogen gas, with no stars capable of igniting sustained fusion, as stars require heavier elements to act as catalysts in their nuclear furnaces. Conversely, if the strong force were just a few percent stronger, its grip would become far more powerful. Protons and neutrons would bind together with such ferocity that they would essentially all fuse into enormous, stable nuclei. In such a universe, the process of nuclear fusion inside stars would be catastrophically efficient, consuming all hydrogen fuel almost instantly. Stars would burn out in a cosmic flash, leaving no time for planetary systems to form and evolve. Furthermore, with all protons bound up in heavy elements, there would be no free hydrogen and thus no water, the universal solvent essential for life as we know it. This perfect calibration becomes even more astonishing when we look at a specific, life-enabling example: the formation of carbon. Inside the hearts of stars, the process of nucleosynthesis is a delicate chain of events. First, hydrogen fuses into helium. Then, two helium nuclei can fuse to form a highly unstable beryllium-8 nucleus, which normally falls apart in a fraction of a second. For carbon to form, a third helium nucleus must collide with this fleeting beryllium-8 before it disintegrates. The odds of this happening are astronomically low unless there is a helping hand. That helping hand is a phenomenon known as resonance. The carbon-12 nucleus just happens to have a resonant energy state that perfectly matches the combined energy of the beryllium-8 nucleus and a colliding helium nucleus. This resonance acts like a catcher's mitt, dramatically increasing the probability of the collision, resulting in a stable carbon-12 atom. This resonance is not a random accident. It is a direct consequence of the precise strength of the strong nuclear force. If that force were even minutely different, the energy levels within the carbon nucleus would shift. This resonant state would disappear, and the triple alpha process would fail. Stars would be unable to produce significant amounts of carbon, and the universe would be devoid of carbon-based life. The physicist Freeman Dyson famously pointed out that this resonance appears to be a put-up job, as if the laws of physics were consciously designed to make carbon abundant and allow for our existence. The strong force's precise value doesn't just enable the building blocks of life, it also governs the most violent and creative events in the cosmos, supernova. When a massive star exhausts its nuclear fuel, its core collapses under its own immense gravity. The strength of the strong force determines how iron nuclei, the end point of stellar fusion, behave under this incredible pressure. At a critical moment, the repulsive core of the strong force, which prevents protons and neutrons from merging completely, triggers a rebound effect. This rebound against the inward rush of material creates a shockwave that blasts the star's outer layers into space in a titanic supernova explosion. It is this very explosion that forges elements heavier than iron, like gold, silver, and uranium, and scatters them across the interstellar medium. If the strong force were weaker, the core might collapse directly into a black hole without a rebound, silently swallowing all the star's heavy elements. If it were stronger, the explosion might be too weak to expel these newly forged elements, locking them away forever. The strength of this force is the difference between a universe enriched with the elements for rocky planets and a universe that is chemically barren. This incredible interdependence shows that the constants of nature are not isolated dials that can be turned independently. They are part of a deeply interconnected web. The strength of the strong nuclear force is exquisitely balanced with the strength of the electromagnetic force, the force of gravity, and the properties of other particles. Altering one requires recalibrating all the others to maintain a universe capable of complexity. This fine-tuning on a nuclear level is what allows for the existence of stable atoms, diverse elements, sustainable stars, and life-giving supernova. It is the reason our universe is a vibrant chemical laboratory and not a monotonous void. This precise and powerful force, operating silently within the heart of every atom, has set the stage for the entire cosmic drama, from the first stars to the planet we call home. Its unwavering strength is a testament to the fact that the laws of physics themselves appear to be written with a purpose, allowing for the possibility of discovery and life in a cosmos that is anything but random. Deep within the heart of every star, a seemingly impossible feat is performed millions of times every second, a miracle of quantum mechanics that literally makes our world possible. This is the 15th cosmic coincidence, the absolutely critical role of quantum tunneling in stellar fusion. At the core of our Sun, temperatures soar to a staggering 15 million degrees Celsius, creating a chaotic plasma where protons, the nuclei of hydrogen atoms, hurtle around at tremendous speeds. These protons are all positively charged, and according to the classical laws of physics, they should violently repel each other, never getting close enough to fuse. The electromagnetic force that pushes them apart creates a powerful energy barrier like a steep, insurmountable hill. For two protons to fuse and kickstart the process that powers a star, they would need to collide with enough energy to literally climb over this hill. The problem is, the temperature at the Sun's core, while unimaginably hot to us, is still far too cool to provide protons with the energy needed to overcome this electrostatic repulsion. By all classical accounts, stars like our Sun should not shine. They should be dark, inert balls of gas. This is where the bizarre and counterintuitive world of quantum mechanics provides the solution. In the subatomic realm, particles do not behave like tiny billiard balls with definite positions and trajectories. Instead, they are described by probability waves. One of the strangest consequences of this is a phenomenon called quantum tunneling. Imagine you're walking toward a solid brick wall. Classically, you would need to muster enough energy to climb over it. But in the quantum world, there's a very small but non-zero probability that you could simply appear on the other side without ever going over the top, as if you had tunneled through it. This isn't science fiction, it's a well-documented and essential process. In the stellar core, a proton's probability wave allows it to have a chance of existing on the other side of that immense electrostatic barrier, effectively teleporting into the tight embrace of another proton just long enough for the strong nuclear force, which only works at extremely short ranges, to take over and bind them together. This is the secret ignition switch for stars. Without quantum tunneling, the the nuclear fires that have burned for billions of years would simply never have been lit. The probability of any single proton successfully tunneling is, by itself, incredibly small, but the core of a star is a numbers game of almost incomprehensible scale. The Sun's core contains a seething ocean of protons, and the sheer density ensures that these unlikely quantum events are happening constantly. Physicist George Gamow was a pioneer in calculating these probabilities, providing the crucial mathematical framework that showed how stars could indeed fuse hydrogen at their observed rates. The rate of this tunneling-driven fusion is not arbitrary. It is perfectly matched to the conditions inside a main sequence star. It proceeds at a pace that is stable and sustainable over billions of years, providing a steady, life-giving output of energy. If the probability of quantum tunneling were significantly lower, the fusion rate would be too slow. Stars would be dim and cool, burning through their hydrogen fuel so lethargically that the universe would still be in its infancy, filled with faint red dwarf stars. Planets orbiting them would be cold and dark, their surfaces locked in permanent ice ages, utterly inhospitable to life. The long, stable lifetime of a star like our Sun, which provides the consistent energy needed for evolution to work its slow magic, is a direct gift from the precise value of this quantum probability. On the other hand, if quantum tunneling were just a bit more probable, the consequences would be equally catastrophic, but in the opposite direction. Fusion would become far too efficient. Protons would tunnel through the energy barrier with reckless abandon, causing stars to burn their hydrogen fuel at a ferocious rate. Instead of shining steadily for 10 billion years, a star like our Sun would explode in a spectacular outburst after only a few million years, a cosmic firework that would quickly fizzle out. The universe would be filled with the brief, brilliant flashes of these short-lived stars, but there would be no long-term stability. There would be no time for planets to slowly coalesce from the debris of previous stellar generations, no time for those planets to cool and form oceans and atmospheres, and certainly no time for the intricate, multi-billion-year process of biological evolution to unfold. The universe would be a thrilling but ultimately barren spectacle of transient light. The fact that the quantum mechanical rules allow for tunneling at precisely the rate needed for stable, long-lived stars feels, once again, like a remarkable and fortunate calibration. This quantum process does more than just keep stars shining. It is the first and most crucial step in the grand chain of nucleosynthesis that builds the elements of the periodic table. The initial proton-proton fusion triggered by tunneling begins a reaction chain that eventually forges helium. In more massive stars, this process continues, using the carbon-nitrogen-oxygen cycle to achieve the same result. The energy produced by this fusion counteracts the immense force of gravity trying to collapse the star, creating a beautiful, stable equilibrium that can last for eons. During this long, stable period, stars act as cosmic alchemists. When they eventually exhaust their hydrogen fuel and move on to fusing heavier elements, they create the carbon, oxygen, nitrogen, and iron that are the fundamental building blocks of planets and life. All of this heavy element production hinges on that first, improbable quantum tunneling event that allows two protons to defy their electromagnetic repulsion and unite. We are therefore not just beneficiaries of stellar energy. We are literally made of atoms that were forged in stars whose very existence depended on a quirk of quantum physics. Our connection to the cosmos is not merely poetic, it is subatomic, so we are left to ponder a deeply mysterious question. Is the precise probability of quantum tunneling, a value dictated by the fundamental constants of the universe, merely a lucky break? Did we just happen to win the cosmic lottery, ending up in a universe where the rules of the quantum world allow for stable stars and long timescales? Or does this exquisitely tuned rate point toward a deeper pattern, a consistency in the fine-tuning that suggests the laws of physics themselves are arranged in a coherent, life-allowing framework? The phenomenon of quantum tunneling is not some obscure, theoretical idea. It is a practical, observed process that is essential for the universe to function as it does. It connects the weirdness of the quantum world directly to the grandest scales of cosmic evolution, proving that the smallest rules can have the largest consequences. This delicate interplay between the probabilistic nature of particles and the deterministic burning of stars is a masterpiece of physical law, a hidden mechanism without which the cosmos would be dark, cold, and devoid of the complexity that leads to us. While the sun's core relies on the bizarre rules of quantum tunneling to shine, our own planet possesses a different kind of inner fire, one that generates not light, but an invisible shield of immense importance. This brings us to our 16th cosmic coincidence, the remarkable stability and protective power of Earth's magnetic field. Imagine a constant, invisible barrage of high-energy particles streaming from the sun, a hurricane of radiation known as the solar wind. Without protection, this relentless onslaught would slowly but surely strip away our atmosphere, ionizing its molecules and blasting them off into space. This is not mere speculation. It is the tragic fate that befell our neighboring planet Mars. Billions of years ago, Mars was a warmer, wetter world with a thicker atmosphere and likely even rivers and lakes on its surface. But when its molten iron core cooled and solidified, its planetary dynamo, the engine that generates a magnetic field, shut down. Without that protective magnetic shield, the solar wind had unimpeded access to the Martian atmosphere, systematically eroding it over eons until the planet became the cold, desiccated desert we see today. Earth, by a breathtaking cosmic fortune, has managed to keep its engine running. This life-preserving shield is generated deep within our planet, in a place of unimaginable heat and pressure. At the center of the Earth lies a solid inner core of iron and nickel, roughly the size of the Moon. Surrounding it is a vast, churning ocean of molten metal, the outer core. This liquid metal is in constant, turbulent motion, driven by two powerful forces: the heat rising from the inner core's slow solidification, and the rotational energy of the Earth itself. This combination creates a self-sustaining process called the geodynamo. As the electrically conductive molten iron moves across pre-existing weak magnetic fields, it generates electrical currents. These currents, in turn, produce and amplify the planetary magnetic field in a fantastic feedback loop that has been operating continuously for at least 3.5 billion years. The stability of this process is nothing short of miraculous. It requires a perfect balance, a core that is still hot enough to remain largely molten, a rotation rate that provides just the right amount of spin to organize the convection, and a composition that allows for efficient electrical conduction. This intricate planetary machinery has operated with remarkable consistency, ensuring that the magnetic shield has never permanently failed throughout the entire history of complex life on Earth. The strength of this field is also fine-tuned to a degree that inspires awe. It is powerful enough to deflect the vast majority of the solar wind, carving out a protected bubble in space known as the magnetosphere. This bubble stretches for tens of thousands of kilometers on the sunward side and trails off into a long magnetotail on the opposite side, acting as a cosmic windsock. When particularly intense bursts of solar particles, called coronal mass ejections, slam into our magnetosphere, we witness the most beautiful side effect of this protective interaction, the auroras. The northern and southern lights are not just a dazzling light show. They are visual proof of our magnetic field at work, channeling these energetic particles toward the poles where they safely excite molecules in the upper atmosphere, causing them to glow. However, if our magnetic field were significantly stronger, it could itself become a problem. An excessively powerful field might interact with the atmosphere in disruptive ways or even influence the chemistry of the planet's surface in unforeseen negative ways. The field we have is strong enough to be an effective defender, yet gentle enough to be a benign presence. This does not mean our magnetic field is static. Throughout Earth's history, the magnetic poles have wandered and the field's strength has fluctuated. Most dramatically, the field has undergone full reversals, where the north and south magnetic poles swap places. Geologic records show these reversals have happened hundreds of times, with the last major one occurring about 780,000 years ago. During these transition periods, which can last for a few thousand years, the magnetic field can weaken significantly, becoming a multipolar, messy field rather than a clean dipole. While a weakened field would offer less protection from solar and cosmic radiation, the geological evidence suggests these periods did not cause mass extinctions. Life persisted, though it might have been a more challenging time for organisms on the surface. Today, scientists are closely monitoring a well-documented weakening of the field in a region called the South Atlantic Anomaly, and the magnetic North Pole is moving faster than ever before. While these are likely part of the natural, dynamic behavior of our planet's core, they serve as a potent reminder that our magnetic shield is not a guaranteed constant. It is a dynamic, living system, and its continued stability is a non-negotiable requirement for the long-term preservation of our atmosphere and the habitability of our world. This invisible force field, generated by a furious ocean of molten metal deep beneath our feet, is a silent guardian whose constant, vigilant presence is one of the most underappreciated and vital coincidences making our existence possible. Yet this invisible magnetic shield, for all its life-preserving power, is not the only celestial guardian that shapes our existence. Our planet's very rhythm, the steady beat of day and night that governs all life, is itself a gift from a cosmic companion. This brings us to our 17th astonishing cosmic coincidence, the profound influence of the Moon on Earth's rotation. We often admire the Moon for its gentle glow, but its true gift is one of motion and stability. The gravitational tug-of-war between Earth and its satellite acts as a gentle but constant brake on our planet's spin. Billions of years ago, in the chaotic aftermath of its formation, Earth spun at a frantic pace, with a day lasting perhaps only 6 hours. The relentless pull of the Moon's gravity, working through the friction of ocean tides, has gradually slowed this rotation to our current, habitable 24-hour cycle. This deceleration was not an instantaneous event but a slow, meticulous process spanning eons, a cosmic dance that has given our world the gift of time. The consequences of this lunar braking extend far beyond simply giving us longer days. This stable rotational period is a cornerstone of Earth's climate system. A faster spinning planet, like the moonless Venus with its 117-day-long day, experiences ferocious wind patterns and extreme temperature swings between its scorching days and frigid nights. On a world with a short day, weather systems would be chaotic and violent, with little time for the surface to absorb solar energy evenly. The 24-hour day provides a perfect balance, long enough for the sun to warm the land and oceans, but short enough that the night does not plunge the planet into a deep freeze. This diurnal rhythm creates predictable wind patterns, moderates global temperatures, and allows for the stable atmospheric circulation that is essential for a temperate climate. It is this very stability that has allowed life to adapt and thrive. evolving complex biological clocks tuned to the reliable cadence of sunrise and sunset. Perhaps even more crucial than the length of our day is the stability of our planet's tilt. Earth's axis is tilted at about 23.5 degrees relative to its orbital plane, a tilt that gives us our seasons. This angle is not fixed in stone. Without the moon's steadying influence, it would be subject to chaotic and dramatic shifts over millions of years due to gravitational perturbations from Jupiter and the other planets. French astronomer Jacques Lascar has performed sophisticated simulations of the solar system's long-term dynamics, and his work reveals a startling truth. Without our large moon, Earth's axial tilt could wander chaotically between 0 and 85 degrees. Imagine a world where the tilt shifts so extremely that the poles point directly at the sun for millennia, melting ice caps and boiling oceans before flopping over to a new extreme. Such a world would be a climate catastrophe roller coaster, with seasons rendered meaningless and stable environments impossible to maintain. The moon's gravitational pull acts as a counterbalance, damping these oscillations and locking our tilt into a narrow, stable range. This is why we have enjoyed consistent seasons for hundreds of millions of years, a regularity that has provided the long-term climatic stability necessary for complex ecosystems to evolve and endure. This dynamic relationship is a two-way street, a constant exchange of energy. As the moon's gravity pulls on Earth, creating the ocean tides that rise and fall, the friction of this moving water against the seabed drains a tiny amount of energy from Earth's rotation. This lost energy is transferred to the moon, causing it to gradually spiral away from us at a rate of about 1.5 inches per year. This process, known as tidal acceleration, means that in the distant past the moon was much closer and days were even shorter, while in the far future, the moon will be farther away and Earth's day will have lengthened considerably. We exist at a perfect moment in this long-term evolution, a time when the day is long enough for a stable climate, yet the moon is still close enough to appear large in our sky and create significant tides. These tides have been another powerful driver of evolution, creating the intertidal zone, a unique and challenging environment that may have spurred the first life to move from the sea onto land. The moon's gravitational pull has even helped to mix the oceans, stirring nutrients and influencing global ocean currents that regulate our climate. From the daily rhythms of life to the grand scale of geological time, the moon's influence is woven into the very fabric of our world. This leads to a humbling and profound question about our place in the cosmos. How common is such a large, stabilizing moon? The giant impact that created our moon seems to be a relatively rare event in planetary formation. While many planets have moons, most are small captured asteroids or coalesced debris from the planetary disk. Large moons that can significantly influence their planet's rotation and climate appear to be the exception, not the rule. Venus has no moon, Mars has two, but they are tiny, captured asteroids called Phobos and Deimos, far too small to exert any stabilizing influence. This suggests that Earth's unique lunar partnership might be a critical factor in the development of long-lasting, complex life. As we search for habitable exoplanets orbiting distant stars, we must consider not just their distance from their sun, but also whether they have a similar celestial guardian to provide the rotational and climatic stability that has been so essential to our own story. The moon is more than a beautiful sight in our night sky. It is a fundamental architect of our world, a silent partner in the cosmic dance that made our existence possible. Its steadying hand has crafted the conditions for life to flourish, making it one of the most intimate and vital of all the cosmic coincidences we have explored. This elegant architecture of our solar system, with its small, rocky worlds close to the sun and its gas giants holding court in the outer darkness, feels so natural and orderly that it's easy to assume this is how all planetary systems must be arranged. Yet, the discovery of exoplanets has revealed a stunning truth. Our system's layout is not the cosmic standard, but a remarkably fortunate and potentially rare configuration that has been instrumental in creating a safe harbor for life. This is our 18th cosmic coincidence, the specific and stable arrangement of our solar system's planets. The story begins not with the planets in their current positions, but in a chaotic, swirling disk of gas and dust that surrounded our infant sun. According to the leading nebula hypothesis, the planets formed from this disk, with temperature being the great architect of their composition. Close to the hot, young sun, only materials with high melting points, metals and rocky minerals, could condense and accrete, forming the terrestrial planets Mercury, Venus, Earth, and Mars. Farther out, beyond what's known as the frost line, temperatures were low enough for volatile compounds like water, ammonia, and methane to freeze into solid ice grains. These ices, combined with abundant hydrogen and helium gas, could coalesce into the massive cores that would become the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. But this is not the full story. A critical and dynamic chapter involves planetary migration. Modern models like the Grand Tack hypothesis suggest that the early solar system was anything but static. Jupiter, the first giant to form, is thought to have embarked on a dramatic inward journey, migrating towards the Sun due to gravitational interactions with the gaseous disk. This movement would have scattered primordial material, potentially halting the growth of a would-be super-Earth and clearing out a significant amount of debris from the inner solar system. Then, just as it approached the orbit of what is now Mars, Saturn formed and began its own inward migration. The gravitational interplay between these two giants locked them into a resonant orbit, causing them to reverse course and migrate back outward to their present positions. This celestial dance, this tack, like a sailboat changing direction, was a pivotal event. By scattering material inward, it may have delivered the water-rich asteroids and comets that later bombarded Earth, seeding our young world with the oceans that now cover its surface. More importantly, by then moving outward, Jupiter and Saturn vacated the inner solar system, allowing the rocky planets to finish forming in a much calmer and less chaotic environment, free from the gravitational bullying of a nearby giant. This orderly structure, with its clear division between the inner and outer solar system, creates a stable gravitational environment. The asteroid belt, residing between Mars and Jupiter, acts not as a violent shooting gallery, but as a relatively stable boundary. While Jupiter's gravity does occasionally perturb asteroids, sending them on new orbits, its primary role in its current position is that of a gravitational anchor. Its immense mass helps to shepherd the orbits of countless objects, preventing the kind of wild, unpredictable orbital chaos that could lead to frequent catastrophic collisions in the inner solar system. This stands in stark contrast to many of the exoplanet systems we have discovered. A common type of planet found around other stars is the hot Jupiter, a gas giant orbiting terrifyingly close to its parent star, completing a full orbit in a matter of days. The existence of these planets is direct evidence of extreme migration, but unlike Jupiter's helpful grand tack, a hot Jupiter's journey inward is catastrophic. Its gravity would utterly destroy any emerging rocky planets in the habitable zone, either ejecting them from the system, shattering them, or accreting them into its own bulk. Any Earth-like world that tried to form afterward would be impossible. The region is far too hot. Our solar system, with its giants parked comfortably in the cold outer realms, seems to be a much less common arrangement. To appreciate the fragility of our situation, we can look to the TRAPPIST-1 system, a fascinating example located 39 light-years away. It contains 7 Earth-sized planets, and several of them orbit within the star's habitable zone, the region where liquid water could exist. At first glance, this seems like a paradise, a system with more potentially habitable real estate than our own. However, the dynamics are profoundly different. All 7 planets orbit incredibly close to their tiny, cool red dwarf star, with years that last only between 1.5 and 19 Earth days. Their orbits are packed together tightly, gravitationally influencing each other in a delicate, resonant chain. While stable for now, this configuration is incredibly sensitive. The planets are so close that the gravitational pull each exerts on the others is significant, a constant tug of war that requires perfect alignment to maintain balance. Furthermore, these planets are likely tidally locked, with one side perpetually facing the star and the other in eternal darkness, creating extreme temperature contrasts that would challenge the formation of a stable global climate. This is not the calm, spacious, and well-ordered neighborhood that Earth enjoys. Our solar system's planets are spaced widely apart, their orbits largely circular and stable over billions of years, thanks in no small part to the distant, steadying presence of Jupiter acting as the system's gravitational cornerstone. This profound stability, a gift of our specific architectural blueprint, has provided the consistent and predictable environment necessary for life to not only emerge but to evolve and thrive for eons, setting the stage for us to eventually look up and ponder the age of the universe that made it all possible. But this grand architectural stability, this perfect arrangement of planets, would be meaningless without the one ingredient that truly allows a universe to become complex and alive: time. This brings us to our 19th astonishing cosmic coincidence, the universe's current age, a narrow window of cosmic opportunity that is both old enough and young enough for us to exist. We live in a universe that is approximately 13.8 billion years old, a number so vast it defies human comprehension. Yet, from a cosmic perspective, this age represents a very specific and privileged moment in the entire lifespan of the cosmos, a sweet spot between a sterile infancy and a barren future. In its earliest epochs, the universe was far too hot and dense for any structure to form. It was a searing plasma of fundamental particles, expanding and cooling from the initial fireball of the Big Bang. For hundreds of millions of years, there were no stars, no galaxies, and no elements beyond hydrogen, helium, and trace amounts of lithium. The cosmos was a simple, empty, and dark place, waiting for the first seeds of structure to grow. The key to our existence lies in the fact that the universe is old enough to have hosted multiple generations of stars. The first stars, known as population 3 stars, were behemoths hundreds of times more massive than our Sun and composed only of the pristine hydrogen and helium forged in the Big Bang. These giants lived fast and died young, burning through their nuclear fuel in only a few million years before ending their lives in cataclysmic supernova explosions. It is in the furious hearts of these first stars and in their violent deaths that the story of our material existence begins. Through the process of nucleosynthesis, these stars fused hydrogen and helium into heavier elements like carbon, oxygen, nitrogen, and iron. When they exploded, they blasted these newly forged elements out into the interstellar medium, enriching the primordial gas clouds with the raw materials for planets, oceans, and life itself. Our solar system and our very bodies formed from this stardust, the ashes of countless generations of long-dead stars. This recycling process required time, billions of years of stellar birth, life, and death to produce enough heavy elements for rocky planets like Earth to coalesce. A younger universe would have been chemically too primitive for our kind of world to even exist. Yet, while the universe is old enough for this alchemy to have occurred, it is also crucially young enough that the accelerating expansion driven by dark energy has not yet ripped the cosmos apart. This is the other side of the temporal coin. Dark energy is causing the expansion of the universe to accelerate, pushing galaxies away from each other at an ever-increasing rate. In the far, far future, this acceleration will have profound consequences. Cosmologists like Martin Rees refer to our current era as the cosmic time window for life because it sits between these two barren extremes. In the distant future, trillions of years from now, the acceleration will have become so dominant that any galaxies beyond our own local group will have been pushed beyond our observable horizon. The night sky will become utterly black and empty. New star formation will cease as the raw gas needed to create them becomes too diffused to collapse. The universe will become a colder, darker, and lonelier place, filled with dying stars and black holes, a cosmos where the conditions for life are impossible. We exist in a golden age of galaxy formation and stellar activity, a time when the universe is still vibrant and full of light, yet mature enough to be richly seeded with the elements of life. This places our emergence in a context that is both humbling and awe-inspiring. Could intelligent life arise at a different cosmic time? It seems incredibly unlikely. Much earlier, and the necessary heavy elements would not have been available. Much later, and the accelerating expansion would have isolated island galaxies, preventing the exchange of materials and making the universe a far more isolated and inhospitable place. The fact that we find ourselves at this precise moment when the universe is still transparent, filled with observable galaxies, and brimming with the products of stellar evolution feels less like a coincidence and more like a necessary condition for our own existence. It forces us to confront the anthropic principle in a temporal sense. We can only observe the universe at a time compatible with our existence as observers. This cosmic timing is not just a backdrop for our story. It is an active and essential character in it, a silent architect that has carefully prepared the stage over billions of years for the entrance of life, setting the stage for us to finally look up and begin to unravel the profound connections between the laws of physics themselves. But this grand cosmic timeline, this perfect age that allows for both elemental richness and observable structure, is itself built upon a foundation even more fundamental and mysterious. The universe's ability to host life doesn't depend on just one or two lucky constants. It relies on an entire symphony of physical laws and fundamental numbers playing in perfect, interdependent harmony. This brings us to our 20th astonishing cosmic coincidence, the profound and precise interdependence of nature's constants. Imagine the universe as a complex and delicate machine with dozens of control dials. Each dial represents a fundamental constant: the speed of light, the strength of gravity, the mass of an electron, the charge of a proton, Planck's constant. The truly mind-bending fact is that these dials are not set independently. They are all exquisitely linked. Turning just one dial even a fraction of a percent would throw the entire system into chaos, rendering the universe lifeless. It is this interconnected web of perfect values that allows for the existence of atoms, chemistry, and ultimately us. To truly grasp this, we must move beyond the constants themselves and look at the dimensionless numbers they create. These are pure numbers without units, formed by combining the fundamental constants. The most famous is the fine structure constant we discussed earlier, approximately 1 over 137, which governs the strength of electromagnetism. But there are others, like the proton-to-electron mass ratio, which is about 1,836. This number dictates the size and stability of atoms. If it were much different, the intricate dance of electrons around atomic nuclei would fail, and chemistry as we know it would be impossible. The gravitational coupling constant, which measures the strength of gravity relative to the other forces, is another crucial example. Gravity is astronomically weaker than the other forces. It is about 10 to the power of 36 times weaker than the electromagnetic force. This incredible weakness is not a flaw, it is a feature. If gravity were significantly stronger, stars would burn through their fuel at a ferocious rate, collapsing into black holes after only a few million years, leaving no time for planets to form or life to evolve. Conversely, if it were even weaker, it would be unable to pull together the vast clouds of gas that collapse to form stars and galaxies in the first place. The cosmos would remain a thin, expanding haze of hydrogen, devoid of all structure. This delicate balance extends to the largest scales of the cosmos through the cosmological constant, the value that describes the strength of dark energy. As we saw, this number is fine-tuned to an accuracy of 1 part in 10 to the power of 120. This is arguably the most precise fine-tuning in all of physics. If this number were slightly larger, the repulsive force of dark energy would have dominated too early, preventing any galaxies from ever forming. If it were slightly smaller and negative, the universe would have collapsed back on itself long ago. The fact that this number is so perfectly calibrated to allow for billions of years of galaxy formation before the acceleration begins is a coincidence that staggers the imagination. It suggests a universe that is not only set up for structure, but set up for structure that persists for an incredibly long time, providing the extended window necessary for biological evolution to run its course. Thinkers like the cosmologist John Barrow have spent their careers exploring this interconnected web. They argue that we do not live in a universe where constants can be tweaked in isolation. Changing one requires recalibrating all the others to maintain a habitable cosmos, and often, no such recalibration is possible. For instance, if you tried to make gravity stronger to allow for smaller stars, you would also be making stars burn hotter and faster, shortening their lifetimes below the threshold needed for life. If you tried to increase the strength of the strong nuclear force to make element formation easier, you might inadvertently make protons and neutrons bind together too tightly, eliminating hydrogen altogether and preventing the long-term fusion that powers stars. The constants exist in a state of mutually reinforcing balance, a cosmic conspiracy where each value depends on the others to create a stable, complex, and life-allowing whole. This is not a system that appears to have been assembled by chance. It has the hallmarks of a deeply integrated and coherent design, where every part is perfectly fitted to every other part. This realization that the laws of physics themselves are a single, unified, and finely tuned entity brings us to the most profound question of all. How did a universe with such breathtaking internal consistency and such a clear capacity for generating complexity and awareness ever come to be in the first place? And so we arrive at perhaps the most personal and profound coincidence of all, one that turns our gaze inward from the vast cosmos to the very nature of our own awareness. We've explored a universe fine-tuned with impossible precision for the existence of life, but it presents us with an even deeper mystery. The universe is not only habitable, it is also profoundly comprehensible. This is the astonishing emergence of consciousness in an understandable cosmos, a phenomenon that allows us to not only exist within the universe but to look out and decode its deepest secrets. The legendary physicist Albert Einstein himself marveled at this, calling it the most incomprehensible thing about the universe that it is comprehensible at all. Why should the human mind, a product of blind evolution on a tiny rock orbiting an average star, be capable of grasping the laws that govern black holes, the birth of stars, and the expansion of spacetime itself? This is not a trivial question. It strikes at the very heart of our relationship with reality. This concept is often explored through a stronger version of the anthropic principle. While the weak version simply states that we observe a universe compatible with our existence, the strong version suggests something far more radical, that the universe's fundamental constants and laws might be specifically tailored not just for life, but for the emergence of conscious observers capable of understanding it. In this view, the universe is built with a kind of built-in knowability. Its laws are not arbitrary, chaotic, or utterly alien. They are logical, consistent, and expressible in the language of mathematics. Think about the incredible power of a simple equation like E equals mc squared. This concise formula, scribbled on a page, describes the relationship between energy and matter that powers every star in the sky. It is a key that unlocks the workings of the cosmos, and it came from the human mind, from Newton's laws of motion that predict the paths of planets to the complex equations of quantum mechanics that describe the behavior of subatomic particles. We have repeatedly found that the universe operates according to a rational set of rules that our minds can discover and model. This comprehensibility relies on a breathtaking congruence between the external world and our internal cognitive architecture. Our brains, with their billions of interconnected neurons, have evolved to recognize patterns, deduce cause and effect, and build models of reality. But the universe itself seems to cooperate in this endeavor. It presents us with consistent, repeatable phenomena. The force of gravity works the same way today as it did a billion years ago. The speed of light in a vacuum is constant. Hydrogen atoms on the other side of the universe emit and absorb light at exactly the same frequencies as they do here on Earth. This reliability and uniformity are what make science possible. Without this cosmic consistency, the universe would be a shifting, unpredictable chaos where no knowledge could be permanently gained. The very fact that we can perform an experiment today and be confident that someone on another planet could replicate it tomorrow is a testament to this deeply ingrained orderliness. Consider the historical arc of scientific discovery. It is a story of humans gradually cracking a cosmic code. Johannes Kepler, studying the precise astronomical data painstakingly collected by Tycho Brahe, didn't just see a random scattering of dots in the sky. He discerned the elegant elliptical orbits of the planets. He found a mathematical pattern hidden within the apparent chaos. Centuries later, James Clerk Maxwell unified the forces of electricity and magnetism into a single, beautiful set of equations that predicted the existence of radio waves. He deduced a fundamental truth about the universe purely through mathematical reasoning before anyone could experimentally detect it. And of course, Einstein's theory of general relativity described the force of gravity not as a mysterious pull, but as the curvature of spacetime itself, a concept so revolutionary it reshaped our entire conception of reality. In each case, the human mind successfully mapped an aspect of the universe's inherent logical structure. This leads to a humbling and awe-inspiring possibility that our ability to do theoretical physics and cosmology might be an unintended or perhaps intended consequence of the universe's fundamental design. The same laws that allow for the formation of galaxies and the nucleosynthesis of carbon in stars also generate a logical framework that a sufficiently complex information processing system, a brain, can eventually decode. We are not passive inhabitants of the cosmos. We are the universe's way of becoming self-aware, of reflecting upon itself and understanding its own origins and nature. This doesn't necessarily imply a conscious designer. but it does suggest a universe whose parameters are set in such a way that the emergence of conscious, comprehending observers is not just a happy accident, but a fundamental feature woven into the fabric of existence from the very first moment. As we stand at the precipice of this realization, it naturally compels us to look outward and wonder if other minds might be engaged in the same grand endeavor of cosmic discovery, and whether the universe might have left other kinds of clues for us to find. Yet as we ponder the profound connection between consciousness and the cosmos, we are inevitably drawn to a moment that tested the very limits of that connection, a fleeting signal from the depths of space that seemed to shout a deliberate hello. This brings us to the 22nd astonishing cosmic coincidence, the enigmatic and utterly unexplained wow signal. On a quiet Ohio evening in August 1977, a radio telescope known as the Big Ear, operated by Ohio State University as part of the Search for Extraterrestrial Intelligence program, was silently scanning the skies. Its method was systematic, patient, and unglamorous, parsing the cosmic static for any anomaly that stood out from the background noise. Then, on August 15th, it happened. The telescope's computer printout, which recorded signal intensity with alphanumeric codes, began to spit out a sequence that would become legendary. As volunteer researcher Jerry Amon pored over the data the next day, his eyes locked onto a string of characters that made his heart skip a beat, 6EQUJ5. Circling it in red pen, he simply wrote "Wow" in the margin, giving the signal its immortal name. What he was looking at was a radio burst of unprecedented strength, a narrowband signal that screamed above the noise, precisely matching the profile that scientists had predicted for an artificial, intentional transmission from another star. The characteristics of this signal are what make it so compelling and so frustratingly mysterious. It was a narrowband signal concentrated around one specific frequency, 1420 MHz. This is no random piece of cosmic static, which is typically spread across a wide range of frequencies. This was a focused beam, the kind of signal a transmitter would produce. Even more tantalizing is the frequency itself. It falls within a protected band of the radio spectrum known as the hydrogen line, a quiet zone where human-made transmissions are restricted. This frequency is significant because hydrogen is the most common element in the universe. Pioneers of SETI like Philip Morrison and Giuseppe Cocconi had suggested that any technologically advanced civilization attempting to communicate across the interstellar void would likely use this universal landmark as a natural calling card, a cosmic hailing frequency that any listening species would recognize. The wow signal's intensity was also extraordinary. On a scale where background noise might register at a level of 1 or 2, this signal peaked at a stunning 30 sigma, meaning it was 30 times louder than the ambient noise of space. It was a shout in a library, a blast of clarity that lasted for exactly 72 seconds, the precise duration the Big Ear telescope could hold a fixed point in the sky due to Earth's rotation. It appeared, rose to a peak, and then faded away with perfect symmetry, exactly as you would expect from a distant, stationary source passing through the telescope's fixed field of view. The search for an explanation has become a 45-year-long exercise in scientific frustration and fascination. Jerry Amon himself spent decades trying to find a prosaic cause, but every hypothesis has fallen short. It wasn't a secret military transmission. The frequency and location don't match any known human activity. It wasn't a reflection of a signal from Earth bouncing off a piece of space debris. The frequency was protected, and no such satellite was in the right position. For years, a popular theory pointed to a passing comet. In 2017, an astronomer proposed that the signal could have been caused by the hydrogen clouds surrounding two comets that were in the approximate region of the sky at that time. However, this theory was quickly dismantled. These comets were not in the telescope's field of view on that specific night, and more critically, comets do not emit strong, narrowband radio signals at the 1420 MHz frequency. The signal's pinpoint frequency and its clean, narrowband nature rule out virtually all known natural astrophysical phenomena. Pulsars, supernova, and other cosmic events produce wideband radio noise, not a pure, focused tone. This leaves only two unsettling possibilities. Either it was an incredibly rare and unknown type of natural event, a one-off cosmic fluke that we have never observed before or since, or it was exactly what it looked like, a deliberate, artificial broadcast. The fact that the signal was never heard again, despite numerous and more sophisticated searches targeting the same area of the sky, only deepens the mystery. The SETI Institute, using powerful arrays like the Allen Telescope Array, has repeatedly pointed its dishes toward the constellation Sagittarius, scanning the same coordinates with far greater sensitivity than the big ear could muster. The result has been a profound and echoing silence. Experts like Seth Shostak, senior astronomer at the SETI Institute, often note that the WOW signal remains the best candidate we have ever received, yet its solitary nature defies easy interpretation. If it was a beacon from an alien civilization, why did it only transmit once? Was it a targeted message that swept past us, never to be repeated? Was it a catastrophic event like the destruction of a vast transmitter? Or was it simply a message not meant for us, a cosmic communication between two other points in the galaxy that we inadvertently intercepted for one brief, glorious minute? The silence that followed transforms the WOW signal from a potential hello into something even more profound and haunting, a cosmic coincidence of the highest order. It was a message that arrived at the right time, at the right frequency, on the one right planet with the technology and the curiosity to notice it, and then it vanished without a trace, leaving behind only a circled annotation on a faded printout and a question that has echoed for decades. It stands as a perfect symbol of our search for meaning in the cosmos, a single data point that is either the most important signal in human history or the universe's most compelling and cruelest practical joke, reminding us that the greatest mysteries are often those that refuse to be solved. Yet amidst the search for deliberate signals from the stars, we find a different kind of message woven into the very fabric of reality itself, a silent, mathematical language that appears in the whirl of a galaxy and the curl of a fern. This is the 23rd cosmic coincidence, the mysterious and pervasive presence of the Fibonacci sequence and the golden ratio throughout nature and the cosmos. This pattern begins simply with the numbers 0 and 1, and each subsequent number is the sum of the two before it, creating a sequence that unfolds as 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on into infinity. Divide any number in this sequence by the one before it, and as the numbers grow larger, the result converges on an irrational number approximately equal to 1.618, known as the golden ratio or phi. This ratio, denoted by the Greek letter phi, has been celebrated for millennia as the epitome of aesthetic perfection, but its appearance is far more than artistic. It is a fundamental principle of growth and structure that the universe seems to employ again and again. We see this mathematical signature in the most breathtaking of cosmic structures. Spiral galaxies, like our own Milky Way, often display arms that unwind according to a logarithmic spiral, a shape whose growth factor is perfectly described by the golden ratio. This is not merely a beautiful accident. It is the most stable and efficient configuration for a rotating disk of stars and gas to maintain its structure over billions of years, resisting the gravitational forces that would otherwise tear it apart. The same spiral pattern emerges in the terrifying beauty of a hurricane, seen from space, where the winds coil into a familiar Phi-inspired shape as the storm organizes itself into the most efficient energy-dissipating form. Even the path of a fearsome lightning strike, forking its way to the ground, often follows the branching pattern of a Fibonacci tree, finding the path of least resistance through the air in a series of optimal splits. These phenomena suggest that this mathematical sequence is not just a human discovery, but a universal law of organization, a preferred solution that nature consistently arrives at when faced with the problem of building stable, efficient, and persistent forms. This pattern reaches its most intimate expression in the biological world, where the drive for efficiency is a matter of life and death. The arrangement of leaves on a stem, known as phyllotaxis, often follows a Fibonacci pattern, with each new leaf emerging at a rotation of approximately 137.5 degrees from the previous one. This specific angle, which is 360 degrees divided by phi squared, ensures that each leaf maximizes its exposure to sunlight while minimizing the shadow it casts on the leaves below. The same principle is spectacularly visible in the seed head of a sunflower. The florets are arranged in opposing spirals, and the number of these spirals will invariably be two consecutive Fibonacci numbers, such as 34 and 55. This flawless packing allows the plant to fit the maximum number of seeds into the smallest possible space, a critical advantage for survival and reproduction. Perhaps the most iconic example is the nautilus shell, whose chambered interior expands in a perfect logarithmic spiral, each new chamber growing by a factor of phi. This allows the creature inside to grow without ever changing its proportional shape, an exercise in perfect, efficient form. Why does this pattern emerge with such consistency across scales from the microscopic to the galactic? The answer lies in a concept known as optimal packing and efficient growth. The Fibonacci sequence and the golden ratio represent a mathematical ideal for organizing components without wasting space or resources. In a sunflower, it prevents gaps and overlaps between seeds. In a galaxy, it allows for a smooth density wave of stars. In a pine cone or a pineapple, the same spiral arrangements achieve the same goal. This is not a conscious design, but rather the inevitable outcome of simple iterative rules playing out over time. A plant's growth hormone, auxin, inhibits new buds from forming too close to it, naturally leading to a spacing that approximates the golden angle. It is a pattern that emerges from physical and biological constraints, a beautiful example of how complexity and order can arise from very simple beginnings. This points to a universe that is deeply mathematical at its core, where the same elegant solutions appear and reappear in utterly different contexts, solving similar problems of structure, growth, and stability. This uncanny recurrence of phi throughout the natural world has led some to see the hand of a divine architect, a conscious design etched into the blueprint of reality. Others see it as a spectacular example of convergent evolution in mathematics, the same optimal solution being discovered independently by unrelated systems because it simply works the best. Whether one sees a grand design or a happy accident of physical law, the effect is the same, a profound sense of wonder at the underlying harmony of the universe. The Fibonacci sequence reveals a cosmos that is not sheer chaos, but a place where chaos gives birth to a deep and resonant order. It is a pattern that connects the spiral of a galaxy to the spiral of a seashell, reminding us that we are not separate from the cosmos, but a part of its ongoing, beautiful calculation. This mathematical thread running through all of creation provides a compelling transition from the patterns we see around us to the ultimate pattern, the specific set of conditions that allowed for the universe itself to burst into being. But this beautiful mathematical harmony we see etched into galaxies and sunflowers finds its ultimate expression in the very first moment of everything, a beginning so perfectly orchestrated it defies all reasonable probability. This brings us to the 24th and perhaps most profound cosmic coincidence, the exquisitely fine-tuned initial conditions of the Big Bang. Imagine the entire universe, all of space, time, matter, and energy, compressed into a singularity of infinite density and temperature. Then, in an instant, it begins to expand. The fate of everything that would ever exist, every galaxy, star, planet, and person, was decided in that first fleeting fraction of a second. The critical parameters were the initial expansion rate, the density of matter and energy, and the overall uniformity. For a universe capable of supporting life to emerge, these values had to be balanced on a razor's edge of unimaginable precision. If the expansion rate had been even minutely slower, the gravitational pull of all that matter would have overcome the outward momentum, causing the entire universe to collapse back in on itself in a big crunch after only a few million years. There would have been no time for stars to form, let alone for life to evolve. Conversely, if the expansion rate had been just a tiny fraction faster, matter would have flown apart too rapidly. The primordial clouds of hydrogen and helium gas would have been too diffuse for gravity to ever pull them together. The cosmos would be a vast, cold, and eternal emptiness, a lonely void without a single star to light it. We exist because the initial kick was perfectly calibrated, a cosmic Goldilocks scenario where the expansion was not too fast and not too slow, but just right. This incredible fine-tuning extends to the universe's initial density. The density parameter, known to cosmologists as omega, had to be almost exactly 1. A universe with omega equal to 1 is said to be flat, meaning its geometry follows the standard rules we learned in school, and it will expand forever, but at a rate that slowly approaches zero. Measurements from the cosmic microwave background show that our universe is flat to within 1% accuracy. To achieve this today, the density in the first second of the universe had to be fine-tuned to an astonishing accuracy of 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. To grasp this level of precision, imagine trying to throw a dart from Earth and hitting a 1-inch target on a planet in a galaxy billions of light years away. The odds of getting the density this perfectly right by pure chance are so infinitesimally small that it forces physicists to search for a deeper explanation. The legendary physicist Stephen Hawking wrestled with this problem throughout his career. He calculated that if the rate of the universe's expansion 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present size. He famously questioned why the initial conditions were so incredibly special, pointing to a fundamental mystery at the heart of our origin story. The leading theoretical explanation for this precision is the theory of cosmic inflation, which proposes that the universe underwent a period of hyper-exponential expansion in the first tiny fraction of a second. This inflationary burst would have stretched the fabric of space-time so dramatically that it would have forced the universe toward the critical density, effectively flattening it and smoothing out any irregularities. While inflation is an elegant solution that solves several major problems, including the horizon problem, why the universe looks the same in all directions, it ultimately just pushes the fine-tuning question back a step. For inflation to start and then stop in just the right way to produce our universe, the properties of the hypothetical, inflaton field that drove it must themselves be exquisitely fine-tuned. The mystery of the initial conditions remains. This leads us to the concept of entropy, which is a measure of disorder or randomness. The early universe was in a state of incredibly low entropy, which is an extremely ordered and unlikely configuration. Think of it like a perfectly stacked deck of cards or a room where all the air molecules are spontaneously gathered in one corner. This low entropy starting point is the ultimate reason we have an arrow of time and why complex structures can form. If the universe had begun in a high entropy state of thermal equilibrium, it would have been a featureless, lukewarm soup where nothing interesting could ever happen. The fact that it started in such a special, low entropy state is a coincidence every bit as profound as the fine-tuning of the expansion rate. It set the stage for gravity to create order from chaos, allowing matter to clump into galaxies and stars, which in turn become engines for creating even more complexity and even lower entropy locally, like the intricate structure of a living cell. The universe's infancy was not a random explosion, but a carefully set initial state that made the entire subsequent cosmic drama possible. Faced with this staggering degree of fine-tuning, cosmologists are left with a handful of deeply philosophical possibilities. One is to invoke a multiverse, or a vast ensemble of universes, each with different physical constants and initial conditions. In this view, we simply find ourselves in one of the rare universes where the numbers are right for life. The rest of the multiverse would be filled with failed universes that collapsed immediately or expanded into nothingness. While this is a popular idea in theoretical physics, it remains entirely speculative with no direct observational evidence. The other possibility, of course, is that the fine-tuning is evidence of some form of design or teleology, that the universe was intended for life. This is not necessarily a religious argument. It could point to laws of physics we do not yet understand that necessarily lead to a life-permitting cosmos. Between an infinite multiverse and a designed universe, we are left with two extraordinary propositions to explain a single, extraordinary fact. Our universe got off to a perfect start. This foundational fine-tuning is the ultimate bedrock upon which all other cosmic coincidences are built, the first and most important roll of the dice that came up all sevens, setting in motion a chain of events that would eventually lead to us looking back and wondering how it was ever possible. This vast and precisely aged cosmos we inhabit presents us with a final, deeply personal coincidence that is defined not by its age, but by its sheer physical scale, the dimensions of our own cosmic backyard, the observable universe. We are living within a sphere of space that stretches an almost unimaginable 93 billion light-years from one edge to the other, a volume so enormous it contains an estimated 2 trillion galaxies. Yet, this colossal size is not arbitrary. It represents a perfect and fleeting window of observability, a Goldilocks zone in both space and time that allows us to see back to the very dawn of everything. This observable horizon is not a physical boundary but a limit set by the fundamental laws of physics themselves. Because the universe has a finite age, approximately 13.8 billion years, and because light travels at a finite, unbreakable speed, we can only see the regions of space from which light has had enough time to reach us. Every star, every galaxy we can possibly detect lies within this immense but finite bubble. The fact that this bubble is as large as it is, yet not infinitely larger, is a coincidence of profound importance for any would-be cosmic observer. The true magic of this scale lies in what it allows us to see. A smaller observable universe would be a tragically limited one. If the cosmos were younger or if the speed of light were slower, our observable horizon would contract. We might see only a handful of nearby galaxies, or perhaps just our own Milky Way. we would have no knowledge of the cosmic microwave background radiation, that faint echo of the Big Bang. The grand tapestry of cosmic evolution, the existence of quasars, the large-scale structure of galaxy clusters and filaments, the very evidence for an expanding universe, would be completely hidden from view. Our science would be built on a tiny, unrepresentative sample of reality, and we would likely conclude that our galaxy was the entire universe, a lonely island in an eternal void. We would be utterly ignorant of the true nature, history, and scale of the cosmos we call home. Conversely, if our observable universe were significantly larger, we would face a different but equally profound problem. This is where the accelerating expansion driven by dark energy becomes crucial. In a static universe, given enough time, the light from every object would eventually reach us. But our universe is not static. It is expanding at an accelerating rate. This acceleration places a fundamental limit on what we will ever be able to see. Galaxies that are currently beyond a certain distance are already being carried away from us by the expansion of space itself faster than the speed of light. Their light, though emitted, will never be able to make progress against the rushing tide of expanding space to ever reach our telescopes. Cosmologist Max Tegmark and others have pointed out that we live in a uniquely privileged era where the observable universe contains a rich variety of structures to study. In the far future, trillions of years from now, the acceleration will have pushed all but the very closest galaxies beyond this ultimate horizon. The night sky for any future civilizations will become utterly black and empty, devoid of any external galaxies. The cosmic microwave background will have redshifted into complete undetectability. Those future astronomers will have no evidence for the Big Bang, for an expanding universe, or for anything beyond their own local group of gravitationally bound galaxies. Their cosmos will appear static, island-like, and fundamentally lonely. Therefore, the 93 billion light-year diameter we observe today is not a permanent feature of the cosmos. It is a snapshot in time, a transient bubble of visibility. We exist at the perfect moment to be cosmic archaeologists. The light that is now arriving at our telescopes has been traveling for billions of years, giving us a direct view into the past. We can see galaxies in their infant stages. We can observe the universe when it was a hot, dense plasma, and we can trace the gradual formation of the large-scale structure that defines the cosmos. This specific size allows for just the right amount of diversity and just the right depth of history to be accessible. It is large enough to show us the universal laws at work. The consistent physics that governs galaxies 10 billion light-years away operates exactly as it does here, yet it is small enough that the finite speed of light has allowed a historical record to be delivered to our doorstep. This vantage point is a gift of unimaginable value, a coincidence of timing and scale that allows a species on a tiny planet to comprehend the entire history of the universe, from its first spark to its present-day grandeur. It connects our fleeting human existence directly to the grandest narrative of all, providing a window into the past that is, by cosmic necessity, precisely the right size for the story to be told. Now consider the remarkable chain of events that allowed us to decipher these cosmic secrets in the first place. The progression of scientific discovery itself unfolds with a timing so impeccable it feels orchestrated, a cascade of breakthroughs where each new insight arrives precisely when the world is ready to receive it and build upon it. This is not merely the steady accumulation of knowledge, but a series of paradigm shifts, as historian Thomas Kuhn described them, that have revolutionized our understanding at a pace that seems almost perfectly synchronized with our technological and intellectual readiness. Imagine if Isaac Newton had been born in an era without the precise astronomical data painstakingly gathered by Tycho Brahe, and interpreted by Johannes Kepler. Without those detailed charts of planetary motion, Newton's genius might have had no foundation upon which to formulate his laws of motion and universal gravitation. His monumental work, the Principia Mathematica, published in 1687, did not emerge from a vacuum. It was the product of a world that had just developed the necessary mathematical tools and a burgeoning spirit of empirical inquiry, allowing him to synthesize celestial and terrestrial mechanics into a single, elegant framework. This pattern of convergent discovery highlights the idea that when the cultural and technological conditions are ripe, breakthroughs seem to emerge simultaneously from multiple minds. The most famous example is the independent invention of calculus by both Newton and Gottfried Wilhelm Leibniz in the late 17th century. Their bitter rivalry aside, this simultaneous emergence suggests that the mathematical world was primed for this new tool. Calculus provided the essential language to describe a universe in motion, and its timing was perfect. Without it, we could not have formulated the laws of physics that govern everything from orbiting planets to falling apples. This phenomenon repeated itself centuries later with the development of quantum mechanics. A perfect storm of unexplained experimental results like the photoelectric effect and atomic spectra converged in the early 20th century, pushing a generation of brilliant physicists like Max Planck, Albert Einstein, Niels Bohr, and Erwin Schrödinger to tear down the classical model of physics and construct a new, bizarre, and profoundly successful quantum framework. They stood on the shoulders of giants, yes, but they also arrived at a historical moment when their specific genius was the key needed to unlock the next door. The tools of discovery have also arrived with uncanny timing. Edwin Hubble's landmark discovery of the expanding universe in the 1920s was made possible by two critical technological advancements. The first was the construction of massive, powerful telescopes like the 100-inch Hooker telescope at Mount Wilson Observatory, which allowed him to observe distant galaxies and resolve individual stars within them. The second was the prior development of spectroscopy, which enabled him to measure the redshift of those galaxies' light. Without either of these tools, his revolutionary conclusion that the universe is expanding would have been impossible. He didn't just have a great idea, he had the right tools at the right time to prove it. In our own era, the digital revolution has catapulted astronomy forward at a breathtaking pace. Modern sky surveys, powered by massive digital cameras and sophisticated software, scan the heavens night after night, collecting terabytes of data that algorithms sift through to find the most fleeting and exotic phenomena, from distant supernova to the subtle gravitational wobbles of stars being tugged by exoplanets. This technological capability has transformed our understanding of the cosmos from a static picture to a dynamic movie, allowing us to observe the universe in real time. This raises a profound question about the nature of progress itself. Is this rapid, interconnected advancement a form of historical inevitability? If Newton had never lived, would someone else have inevitably discovered the laws of gravity within a few decades? Or are we the beneficiaries of a rare and fragile alignment of genius, culture, and technology? The pace is undeniably accelerating. The 2 centuries between Newton's mechanics and Einstein's relativity were followed by a mere few decades before quantum mechanics upended everything again. This acceleration suggests a kind of intellectual compounding interest, where each breakthrough provides more tools and sparks more questions, leading to an exponential growth in understanding. We are living in the golden age of this expansion, a time when our instruments can peer back to the first light of the universe and our theories can describe the behavior of subatomic particles with incredible precision. This fortunate timing of human curiosity and capability has granted us a front-row seat to the greatest show in the cosmos, allowing us to not only witness its wonders but to truly comprehend them. Long before the invention of the telescope or the language of physics, humanity looked up at the night sky and saw not random points of light, but a grand, interconnected story. This profound and ancient impulse to weave celestial phenomena into the very fabric of our myths and legends represents our 27th and final cosmic coincidence, the mysterious and recurring alignment of cosmic events with human mythology. Across vast distances of time and culture, the most dramatic events in the heavens have consistently found their echo in our stories, our religions, and our art, suggesting a deep, perhaps fundamental, connection between the cosmos and human consciousness. This is not merely about primitive people being afraid of the dark. It is about the human mind instinctively seeking patterns and meaning, using the most spectacular events in the natural world as a canvas upon which to project our greatest hopes, our deepest fears, and our most pressing questions about our place in the universe. One of the most enduring examples of this celestial storytelling is the mystery of the Star of Bethlehem. The Gospel of Matthew describes a star that rose in the east and guided the Magi to the birthplace of Jesus, an event that has fascinated astronomers and historians for centuries. While a miraculous, supernatural star is a matter of faith, several plausible astronomical explanations align beautifully with the historical timeline. One compelling theory points to a rare triple conjunction of the planets Jupiter and Saturn in the constellation Pisces, which occurred in the year 7 BCE. To ancient astrologers, Jupiter was known as the king's planet, Saturn was associated with justice and protection, and Pisces was often linked to the lands of the West, including Judea. The sight of these two royal planets dancing together 3 times in a single year in that specific sign would have been interpreted as a powerful omen, a celestial announcement of the birth of a great king in the West. Another captivating theory suggests the appearance of a brilliant new star, a supernova or a nova that shone with sudden, unprecedented intensity. Chinese and Korean astronomical records from around 4 BCE note the appearance of a strange, bright guest star that remained visible for more than 70 days, a beacon in the sky that could have easily been seen as a divine sign. Whether it was a planetary dance or a stellar explosion, the coincidence lies in the timing and the interpretation. A spectacular, real astronomical event provided the raw material for a story that would go on to shape 2 millennia of human culture. Beyond singular events, the predictable yet awe-inspiring cycles of the heavens were also codified into myth. Solar and lunar eclipses were perhaps the most terrifying of these occurrences, as the sun or moon seemed to be violently consumed by some dark celestial beast. In ancient China, the word for eclipse was shi, meaning to eat, and it was believed a great dragon was devouring the sun. The frantic beating of drums and shooting of arrows into the sky during an eclipse was not mere superstition. It was a communal effort to scare the dragon away and save the light of the world. The Vikings told tales of Skall and Hati, 2 wolves forever chasing the sun and moon across the sky, who would finally catch and swallow them at Ragnarok, the end of the world. These stories were more than just fanciful explanations. They were sophisticated psychological tools that transformed a chaotic and frightening event into a narrative with a known outcome. By giving the eclipse a name and a story, ancient cultures gained a sense of understanding and control over the uncontrollable, a way to process the temporary death of a celestial body and ensure through ritual its promised rebirth. The cyclical return of comets provided another powerful source of mythic inspiration, with Halley's Comet being the most famous celestial nomad. Its appearance every 76 years has been meticulously recorded by astonished observers for millennia. When it blazed across the sky in 1066, It was seen as a definitive omen preceding a monumental shift in power. Later that same year, William the Conqueror won the Battle of Hastings and seized the English throne. The Bayeux Tapestry, which chronicles the Norman conquest, famously depicts the comet hovering ominously over King Harold's court, a clear symbol of divine displeasure and impending doom. In the Americas, many native cultures viewed comets not as harbingers of destruction, but as cosmic cleansers or spiritual messengers. This contrast in interpretation highlights a fascinating aspect of this coincidence. The same objective event in the sky could be woven into entirely different cultural narratives, each one reflecting the unique worldview, fears, and values of the people who witnessed it. The comet itself was neutral. The meaning was imposed by us, a testament to our innate need to find significance in the grand theater of the cosmos. The late, great astronomer Carl Sagan spent much of his career exploring this very intersection, most famously in his iconic television series, Cosmos. He argued that this human drive to explain the heavens was the very cradle of science itself. The first astronomers were the priests and shamans who tracked the motions of the stars to create calendars for planting and harvest, who observed the patterns of eclipses and began to predict them. This quest to understand the gods in the sky slowly, over centuries, evolved into a disciplined inquiry into the laws of nature. The wonder and awe inspired by these celestial events were not antithetical to science, they were its original fuel. That sense of wonder is far from dead. In our modern, electrically illuminated world, we may have lost the pristine darkness of our ancestors, but we still gather for meteor showers. Every August, people lie on blankets in backyards and fields to watch the Perseid streak across the sky, sharing in a moment of collective quiet awe. We may now understand that they are just tiny bits of comet dust burning up in our atmosphere, but the experience itself remains magical, a direct connection to the cosmos that transcends explanation and unites us under the same vast sky, just as it did for our ancestors millennia ago. This enduring relationship between the human mind and the cosmos forces a profound reflection. Is this persistent alignment of story and star merely a series of fortunate coincidences, a case of our pattern-seeking brains connecting dots that have no real connection? Or does it point to something deeper, a fundamental human need to see our own narratives reflected in the universe, to feel that we are part of a grand, cosmic story that is still unfolding? The stories we told about the stars were our first attempts to write a user's manual for the universe, and in doing so, we were also writing a manual for ourselves, defining our place, our purpose, and our connection to something infinitely larger. These myths are not lies, they are the language of wonder, the starting point for all exploration. They remind us that science and story are not opposing forces, but two sides of the same human coin, one seeking to understand how the heavens go, and the other seeking to understand what it means for us, the conscious inhabitants of a small planet, living under that same starry sky. As our journey through these 27 astonishing cosmic coincidences comes to a close, one overwhelming truth emerges from the tapestry of evidence. The universe we inhabit displays a level of order and precision that stretches far beyond what we could reasonably attribute to random chance. From the moon's breathtakingly perfect alignment during a total solar eclipse to the inexplicably precise value of the fine structure constant, from the protective embrace of Jupiter's gravity to the ghostly, life-enabling mass of the neutrino, we find ourselves surrounded by a conspiracy of conditions so perfectly calibrated for our existence that it demands a deeper explanation. Each layer of this cosmic fine-tuning, from the quantum realm to the vast architecture of galaxy clusters, points toward a reality that is either unimaginably lucky, astonishingly designed, or one possibility among a near-infinite multitude within a broader multiverse. This profound realization is not an endpoint for curiosity, but rather a magnificent starting point for a lifetime of wonder. These mysteries are far more than abstract scientific puzzles to be solved. They are an open invitation for all of us to become active participants in the greatest story ever told. They call on us to look up at the night sky with fresh eyes, to question the nature of our reality with courage, and to appreciate the breathtaking improbability of our own conscious presence in a universe that seems tailor-made for our arrival. Whether you find yourself drawn to the mathematical elegance of the Fibonacci sequence in a spiral galaxy, or humbled by the delicate balance of oxygen in our atmosphere, each coincidence offers a unique window into the profound interconnectedness of all things. We want to hear which of these cosmic alignments resonated most deeply with you. Was it the protective role of Jupiter, deflecting asteroids away from our fragile world? Or perhaps the mind-bending fine-tuning of the universe's initial conditions that allowed for anything to exist at all? Share your thoughts and personal favorites in the comments below. We read every single one and love to continue the conversation with this incredible community of fellow cosmic explorers. If this journey has sparked your sense of wonder, make sure to subscribe and hit the notification bell so you don't miss our next deep dive into the wonders of space, time, and reality itself. The investigation into our cosmos is the most thrilling adventure humanity has ever undertaken, and it is a story that is still being written. New telescopes peer deeper into space than ever before. Particle accelerators probe the fundamental building blocks of existence, and theories on the nature of consciousness and the multiverse continue to evolve. We are living in a golden age of discovery, where each answered question reveals a dozen new, even more fascinating mysteries waiting just beyond the horizon. So keep asking those big questions, stay curious about the world around you, and never stop looking up. The universe has revealed 27 of its secrets to us, but it holds endless more, just waiting for the next curious mind to uncover them. Throughout our exploration of these 27 cosmic coincidences, a recurring theme has emerged, one that challenges the very notion of a simple dichotomy between pure chance and intentional design. It is the fascinating and paradoxical interplay between chaos and order, a dynamic dance where what appears to be random and destructive often lays the essential groundwork for stunning complexity and life. This is not a universe that is either entirely chaotic or perfectly ordered. It is a system that thrives on the creative tension between the two, using chaos as a sculptor uses a chisel to break away the excess and reveal the form hidden within. Consider the very formation of our solar system, a process that was anything but gentle and predictable. The early solar system was a violent shooting gallery of planetesimals, a chaotic environment of constant collisions and gravitational perturbations. It was from this primordial chaos that the planets themselves were forged. A catastrophic impact like the one that gave birth to our moon seems like the epitome of destructive randomness. Yet, this incredibly violent and unlikely event ultimately provided Earth with a stabilizing influence that regulates our climate and tides, creating the steady rhythms that life came to depend upon. The asteroid impacts that periodically scar planetary surfaces are another example of chaotic violence. While a single impact can cause mass extinction, as it did for the dinosaurs, these same events also deliver water and organic compounds, the very building blocks of life, from the outer solar system to inner worlds like Earth. Chaos in this grand cosmic context is not merely a destructive force. It is a vital delivery mechanism and a catalyst for change, clearing the evolutionary slate to allow for new, more complex forms to emerge. This concept finds a powerful echo in the work of Nobel Prize-winning chemist Ilya Prigogine, who studied what he called dissipative structures. These are complex, ordered systems that can spontaneously emerge out of chaotic conditions, but only when there is a constant flow of energy moving through them. A simple example is a whirlpool in a stream. The water molecules are in constant, chaotic motion, yet they organize themselves into a stable, swirling structure that persists as long as water continues to flow. Prigogine showed that this tendency toward self-organization is a fundamental property of the universe under the right conditions. On a cosmic scale, we see this everywhere. The chaotic motions of gas and dust within a nebula, under the relentless flow of gravitational energy, can collapse into the exquisite order of a solar system. The turbulent, churning plasma in the sun's core, driven by immense pressure and heat, organizes itself into the precise nuclear fusion processes that power the star. The universe, it seems, has a natural inclination to tumble toward order from chaos when energy is applied, suggesting that the emergence of complex, habitable structures might be an inherent potential within the laws of physics, not an inexplicable fluke. This brings us to the famous butterfly effect, a cornerstone of chaos theory which posits that tiny, seemingly insignificant changes in initial conditions can lead to vastly different and unpredictable outcomes. While often used to illustrate how fragile and unpredictable complex systems are, this same principle can be flipped to reveal a profound truth about our existence. The initial conditions of the Big Bang were fine-tuned with impossible precision, but the universe that unfolded from that moment was not a predetermined mechanical clock. The chaotic interplay of quantum fluctuations, gravitational instabilities, and random collisions introduced an element of chance that allowed for creativity and novelty. The specific path that led to our solar system, to Earth, and to us was one of countless trillions of possibilities. A slight gravitational nudge from a passing star a billion years ago, a random mutation in a strand of DNA, the specific timing of an asteroid impact, each of these chaotic events was a fork in the road, and the path we find ourselves on is the result of an almost infinite number of such forks. This perspective doesn't diminish the wonder of our existence, it magnifies it. We are not the preordained outcome of a rigid cosmic blueprint, but the stunningly improbable and beautiful result of a universe that is both law-bound and creative, where order provides the stage and chaos writes the unique and unpredictable play. Therefore, when we marvel at the cosmic coincidences that define our universe, we need not choose between seeing them as mere accidents or evidence of a grand designer. There is a third, perhaps more profound, possibility that we live in a cosmos whose fundamental laws naturally encourage the emergence of complexity and life through the dynamic interplay of chaos and order. The constants of physics set the boundaries of the possible, creating a playing field where self-organization can occur. Within those boundaries, chaos provides the randomness, the variation, and the raw material that allows for experimentation and innovation on a cosmic scale. This duality is not a bug in the system. It is the essential feature that allows the universe to be both stable enough to support life and dynamic enough to actually produce it. It allows us to see the universe not as a static, finished product, but as an ongoing, creative process, one that is still unfolding, still experimenting, and within which we are a conscious, wondering part of that magnificent